Hi everyone, and welcome to this three-day course entitled Introduction to High Performance Computing for Life Scientists. My name is Julian, and I'll be one of the three people running this course, along with Arno Prum. Do you want to say hi?
Hello, everyone.
And Holly Judge.
Hello, everyone.
There we go. This course is run by a number of people, but primarily the three bodies most involved with the creation of this course are the BioXL Consortium, the BioXL Center for Excellence, PRACE, and EPCC. We'll get more to how all three of these people, three of these groups are in a sec. Regarding general information, there are some things that I wanted to make you all aware of. All of the course material is available on the course GitHub page, and I will put a link into the chat. Let's put it in the right chat. All of the course material is available on the course GitHub page here. You will also be able to find the course videos once they're uploaded. If there's any bits you miss or any bits you want to rewatch, you'll be able to find the course links to the course videos on the course web page, which is here. And finally, there are a couple of places where you can post questions or write comments. One of the places is the course Etherpad, which all of you should have access to. The link to the Etherpad is here, and the other place is in the chat where I've posted everything. Right, so with that, that's the wrong one. With that, let's start with the course. So welcome everyone to this course. We're very happy to have you all here. Before introducing the course proper, I wanted to introduce Collaborate. For this course, we will be using Collaborate, which hopefully you've all seen because you're currently on listening to me. So there's a couple of things that you should be made aware of about Collaborate. First of all is there is a purple button in the bottom right corner with two chevron symbols. If you click on that, you will open the, if you click on that purple button, you can open or close the course options. Within those course options, you'll find access to the group chat, where I posted a couple of links and where you can say hi. In case you need it, it's here. You can also find the little cogwheels is settings. If there's anything about Collaborate that you want to change, settings is probably the way to go. And then finally, at the very bottom center of the Collaborate page, under the screen that I'm sharing, you should have an icon for your microphone. If you ever want to turn your microphone on or off, please click it there. Please do try to keep your microphone off while we're in the middle of teaching things, but there will be plenty of opportunities for people to talk and chat chat with each other, and we do really want to get to know as many of you as we can over this course. And the other one that I wanted to mention is there is the hands up symbol, which you can click to put your hand up, and when you put your hand up, the course organizers, we will be modified of that. We will be notified of this, and we will be able to check whether everything is all right. Now we've set up this course to be as reactive as possible. So if you have questions, whenever you have questions, please let us know. We're more than happy to answer them. It's why we're here. So regarding the course structure and methodologies, we've tried to go with a three-pronged approach. We've parts of this course is done in a very carpentry style approach, where there will be hands-on practicals with us talking you through some of the practicals to help you. Parts of it will be done in a more traditional lecture fashion, where there will be slides and we'll talk you through information by going through some slides. And finally, there are some parts which will be done as pre-recorded lectures, which we've made sure to have those sessions happen either right before or right after a longer break, like a coffee break in the morning or a lunch break, so that you'll have time to watch those videos. And then if you choose to, if you realize that you want to watch the videos at double speed, that's because that's how you watch videos on YouTube, that's absolutely fine. Or if you need more time or need to revisit certain things, you can take your time with those videos. The last point I want to raise very quickly before describing the actual contents of the course proper is feedback. Feedback is super important to us. I've already mentioned raising your hands and posting in the chat for any questions that you might have. Please do that. Whenever you have any questions, we'll answer them. There's 3 organizers, so that whenever one of us is speaking, the other 2 organizers are able to answer any questions in the chat. And we've also got another couple of people from BioXL who are here who may be able to answer questions and are more than welcome to. Also, any attendees are more than welcome to answer questions if they think they know the answer. That's absolutely fine. This is a collaborative effort after all. Further to this, after the course, we will be sending a feedback form to all of you, and we would love feedback. This is the first time that we're running this course entirely online, and this is the first time that we're running it in this semi-carpentries, semi-traditional lectures fashion, and any and all feedback that we can get for things that we do well and things that we do bad are very important to us, so that we'll be able to improve this course going forward and also improve any other courses that we give. We all 3 of the bodies that I mentioned before, BioXL, EPCC, and PRACE, have a number of training opportunities, and we really want to make them as good as possible. So, with that, introduction to the life sciences. So hopefully by now you should have seen all of the prerequisites for the course before signing up. But this course is designed to allow any researcher from the computational life sciences to participate in and complete this course regardless of prior experience in high-performance computing. This is a true introduction. We expect no prior knowledge of supercomputing or high-performance computing. We do expect familiarity with the Linux command line, but only very basic commands, such as how to change directories, how to move files, how to edit files within a shell editor, a terminal editor, and how to SSH. There's no programming knowledge necessary, and you will not be expected to program during this course. We've tried to keep this course incredibly practical. There's, I'm not quite sure how many hours of practical sessions there are, but we've tried to keep it as close to 50% us teaching things and 50% you doing things hands-on to really to really give a better understanding of what the course is about. So hopefully that'll come across. So what is the purpose of this course? Well, the primary purpose of this course, the most simple purpose of this course, is to get everyone here to understand what do we mean by high performance computing and what is it used for? Why are you here, essentially? Why would you be interested in this? We'll also cover things like what makes up a supercomputer, the architecture behind that. We'll discuss hardware and software. We'll discuss how computers work, how processes run, and how they are split amongst numbers of cores. We'll also describe what a core is, what a processor is, all that sort of thing. And we'll also discuss a fair bit about parallel computing and how to get the most out of parallel computing, so that your programs, your I don't know, the simulations you're trying to run, the DNA you're trying to read, so that you're able to do all of that efficiently. And because of all of the, and with all of the hands-on practicals, we also hope that you'll be in the process gaining a lot of experience of using HPC machines. For this course, we'll be using ARCHER2, and we'll get to that in a moment. But hopefully you'll get used to running on the UK's national supercomputer, and through that see that it can be quite easy to run on HPC systems, and that might help in your future research. I think I've described most of this. I think I did not mention that we would discuss some of the challenges of running life science pipelines and workflows. And then we'll finish off the course. This is for day 3. We'll finish off the course by describing what HPC facilities are available in the UK and EU, and discuss how HPC in the last couple of years has been changing and evolving, and what it looks like it's changing and evolving into. And with that, that is the end of my introduction and welcome. Again, welcome to everyone for coming here. We're more than happy to have you here, and please, please, please do chat in the chat, say hi. Really happy to get this opportunity to meet and talk to all of you. And at this point, I will pass on to Arno to talk a bit more about EPCC, PRACE, and BioExcel.
Thanks, Julian. I'll just get my sharing in place. Okay, hi everyone. So my name is Arno. I'm based at EPCC, and I'm going to take the opportunity now to just tell you a little bit about the various organizations that are involved in providing this course. This slide mentions Rosna Apostolov. I am not Rosna Apostolov. I have stolen this slide from Rosna Apostolov, my BioExcel colleague, to just tell you a bit about what BioExcel is, first of all. So BioExcel, as Julian already mentioned, is an EU-funded Center of Excellence for High-Performance Computing, and we are focusing specifically on providing software development and support and training and all kinds of activities surrounding computational biomolecular modeling and simulation. So over the past couple of year and a half, or a year or so, we've done COVID-19 work, done by my colleagues. We have a number of use cases that are exploiting high-performance computing using some of the core applications that we support, like Chromax, Haddock, PMX, and CP2K, to perform all kinds of studies of drug design and mutation studies, a variety of areas. We are trying, as a center of excellence focused on the use of high-performance computing, our role is to try and support researchers throughout the EU in using HPC machines that are part of the infrastructure in Europe. 3 examples of which are here on the slide. So that's what it's all about, using these machines to do better science, more complex science, faster. Here are some of the partners involved. There's a lot of countries, a lot of member states are involved. Colleagues in Spain, Germany, Norway, Netherlands, as well as in the UK and in Sweden and other places as well. So we're a hub for biomolecular modeling and simulation. As I already said, we are providing both software development and training and support. And we're focused both on academia and on industry. I already mentioned our core applications. We're also developing workflows that make it easier to deploy our software on a variety of platforms and to reproducibly share workflows, both also on HPC machines. As I said, we're supporting academia and industry, hoping to do that during this session. We're doing a lot of training events. You can see our website. There are a number of courses every year. We have a webinar series. If you go to the website, the BioExcel website, you can see our past webinars. We have a YouTube channel which hosts these as well. We have a support forum where you can ask help with use of any of the software that I just mentioned. And we have a newsletter that you're very welcome to sign up for if you're interested at all in any of the topics that I just mentioned. That's a whirlwind overview of BioExcel. And next, I will tell you about PRACE and let's see. Yeah, ARCHER2, EPCC, and PRACE. So ARCHER2, as Julian already said, is the UK's national supercomputing service. EPCC, where we are based, when I say we, I mean Julian, Holden, and myself, is an organization at the University of Edinburgh, and we physically host ARCHER2 and provide various kind of levels of support for the service. So ARCHER2 is the machine that you'll be using during this course. We provide a number of training courses throughout the year at various locations, although of course since the start of the pandemic it's all been online. This is ARCHER2, which has just recently been, well, last year was gradually built up in our advanced computing facility in a purpose-built building just outside of the city of Edinburgh, where we are based. We have other machines as well, which are used by academia and industry. We're a supercomputing center. We've been around for a while. We're not in Edinburgh. I mean, this course would otherwise be in Edinburgh, but yes, we're unfortunately not able to welcome you here. But the nice thing about being online is we can have people from all over the place, sometimes different time zones. So if this is not good morning to you, then good, whatever your local time zone is. There are various resources for ARCHER2 that you may be interested in, both referring to during the course as well as afterwards. I am not David Henty. Similarly to Rosna Postolov, I've stolen David Henty's slides to tell you about ARCHER2, EPCC, and PRACE. I'm reiterating the fact that we appreciate feedback. We run a master's course in high performance computing and also high performance computing with data science. We have a massive online course as well. It's part of organized under PRACE as well. We'll talk later about the access to ARCHER2. After this course, you will actually retain that. You'll be able to use ARCHER2 during outside of the hours of the course itself, and also after the course days finish. There's no security room because we're not in a room, we're in a virtual room. There's an ARCHER2 code of conduct, which you're encouraged to have a look at. The ARCHER2 service supports software development calls. If you're based in the UK, that might be of interest. Tell you about PRACE. PRACE is an organization it's an EU partnership where member states and associated states collaborate to support use of HPC resources by researchers. So you can see the current member states listed here, and EPCC represents the UK. We have a number of advanced training centers throughout the EU that provide courses, one of which is this course. And yeah, PRACE funds a variety of activities, and if you want to have a look at other training opportunities, I would encourage you to have a look at the link given there at the praceri.eu website. There's quite a lot of training. So with that, I will leave that and indeed agree with what's said here. I hope you find this course really useful. We try to tailor it to what we think are the needs, really concrete, both conceptual and concrete kind of needs to get you into HPC. So with that, I will stop sharing.
So hopefully you can all see my screen. And please do let me know if at any point the text is too small, let me know and I can increase the font quite easily. So this is going to be a pretty quick, brief overview of what we mean. What do we mean by high performance computing? And let's start with a very basic question to all of you. I will go on the course Etherpad and here we go. Could you all please go on the course Etherpad and let me know what you think high performance computing is? If some of you want to answer out loud, or if you want to answer in the chat, please feel free to do so. If you're wanting to answer out loud, please put your hand up. But yeah. So our first answer seems to be using parallel computing. And cool. Mohammed sounds like Mohammed wants to give an answer vocally. Please go right ahead.
Yeah, the idea of high performance computing is that we could, if we could aggregate or combine the power of single computers into a workstation on a cluster, so we can end up with stronger computation power. So it's all
Yeah,
about
that sounds.
aggregating the computational power.
Yeah, that sounds pretty spot on right there as an answer. Using parallel computing to speed up MD simulations. Yes, that's right. The purpose of high performance computing is often to allow highly parallel systems to be run, and that can often be useful for molecular dynamic simulations. Computing with a computer with a high number of resources, also very much true. And we have using a computer cluster composed of many compute nodes to parallelize computational power. Absolutely valid and correct answers. So I give an answer. I can't remember what it was. So high performance computer is just a network of computers in a cluster that typically share a common purpose. So you can get different types of performance computers, some of which are more geared towards machine learning, some of which are more geared towards molecular dynamics, some of which are GPU heavy, some of more CPU heavy. There's lots of flavors of those, and they are used to accomplish tasks that might otherwise be too big for any one single computer. And I noticed during the chat that I noticed during the introductions that there were a lot of molecular dynamics simulators, and we've all anyone who's ever done molecular dynamics will have had that one simulation that you launch thinking it'll, you launch it on a Friday thinking it'll be done on by the Monday, and then 3 months later, or maybe 3 weeks if you're not as quite as patient, it's still running and still local. One of the aims of high performance computing is to allow people to run bigger jobs faster or more quickly by essentially aggregating resources of many computers. So before going into what makes high performance computing, what makes a high performance computer, with what we mean by a parallel machine and a computer cluster. So I'm assuming because you're all in this course that you either all have access to at least a computer or a laptop, and the computer that you're using will most likely have a multi-core processor, unless it's quite old. There will be a hard drive where you're able to store any data that you download or whatever. There will be memory, random access memory, RAM. There will also be an operating system, or at least I hope there will be an operating system. And then there's a couple of other features that you can have. And while modern computers can do a lot, and they are so than 10 or 20 years ago. I remember when I was a kid needing to uninstall the drivers for the floppy disk in order to be able to have enough memory to play Lemmings. That's no longer the case. I mean, no one uses floppy disks. And I'm not that old either, like, early 30s. But still, I remember doing these things. Nowadays, you've got more than enough space like on a phone. But there are still limits to what these computers can do. And computers have been increasing in power, increasing in memory, increasing in so many features over recent years. But we humans still have a knack of whenever we're given something that's bigger, better, faster, we still think, well, okay, that just means I want to do a much bigger simulation. It'll take even longer to run, and now it's still taking forever. So one way to overcome these limits is to pool computers together to create a cluster of computers. And these pooled resources can then be used to run software that might require more total memory. So maybe you were trying to run a simulation that's so large that you didn't have enough RAM to just have it all in cache. I.e., your computer wasn't able to just store all of the positions at any given time, and it would lose time trying to remember where all the are. Or you might want a system that just has more processors so that you're able to get to the next step in your simulation faster in order to finish it in a more reasonable time. So one way to do this is a large number of computers, and I'm actually quite happy that I forget who it was. I think it was, let me see. I think Pedro mentioned that Pedro used a small group cluster at their university. When I was a PhD student, I also used a small group cluster and had to take care of it and learned so much about clusters. It was great fun. But yeah, one of the ways that you can, and this is a picture of it because, you know, always plug the group cluster where possible. One of the ways that you can get better computation power is to take a bunch of computers and just link them together. And so here you've got the cluster, which has the head node here, a number of compute nodes. There's 1, 2, 3, 4, 5 GPU nodes. I'm not too sure what that one is. I think that one's a backup. And they're all linked to right here. You can just about see it. I can zoom in, actually. That's zoomed in too much. There we go. That blue thing right there is the network switch. And the way it works is basically like any Ethernet switch, except essentially you're allowing all of your computers to communicate either directly with one another or directly with the head node, or both, in order to speed up, or in order to allow you to have effectively what acts like a bigger computer than any single one of those individually. So to make this a bit more simple, if you imagine that we had 5 computers and each computer has 4 cores in them, and I'll be describing later, probably later tomorrow rather than today, what I mean by a core, what I mean by a processor. But roughly speaking, a core is a unit onto which you divide work. So whenever you do a job on a computer, you send your job to one or a number of cores. So you've got 5 computers, each of which has 4 cores. And by connecting together, you're now able to run jobs on 20 cores, whereas before you were only able to run jobs on just 4 cores on any computer. So hopefully, if you've set up things sensibly, you should be able to get results from your simulations faster. So this is the group cluster. But while this can increase the speed at which your codes run, or it can allow you to run larger, I'm pretty sure that, and please stop me if I'm wrong, but I'm pretty sure that no one would look at this picture and say, yeah, this is definitely high performance computing. Because it isn't. There's still a couple of things that can be improved to make a better, more powerful, more quick system. What makes, so how do we differentiate a system like this, which is a bunch of computers just put together with shoestring and turn it into high performance? Well, there's really 2 things, 2 or 3 things that really define, you know, a local computer cluster and define what makes a high-performance computer versus a local computer cluster. And these things are just the number of computers and or nodes in your system. A HPC system will have hundreds to tens of thousands of computer nodes. So whereas in this picture there's about 10 to 12 total computers, if we take ARCHER2, the system that you'll be playing around with for this course, ARCHER2 currently has 1,024 nodes. So 2 orders of magnitude more than the local cluster I showed above. And at the moment, it's not even the full ARCHER2 system. In the next couple of months, we'll be increasing it to its final form, which will have 5,585 nodes. So that's one thing that makes a high-performance computer as opposed to a parallel machine or a local cluster. The other thing is the strength of each individual node. HPC systems usually are built with state-of-the-art computers. So for instance, each ARCHER2 nodes has 128 cores. My laptop, for comparison, has 4. And each node has 256 gigs of RAM. I have no idea how much RAM my laptop is because I never need that much on a laptop. These are both very large numbers. For those of you who are into processors, I've actually written down exactly what types of processors they have. But with this criterion, so you know, the strength of each individual computer and the number of computers in your cluster help to define what is a high-performance computer. However, there's one huge downside to the strength of each individual computer and or node being one of the defining factors for HPCs, for high-performance computers, which is because computers get better very, very quickly. You cannot keep a computer node, you cannot say that a computer node is state-of-the-art for very long, which means to keep high-performance computers high performance, you need to change your nodes regularly. And they often get changed every 5 to 10 years. Usually after 5 years, it's already starting to show age and nowhere near as powerful as some of the newer high-performance computers that are coming out. And now the final thing that really makes a high-performance computer. Can I define a node versus a computer? Yep, that's a very good question. If we look at this picture here, as I said, there's a number of computers. There's there's a computer here, and then there's 3 computers next to it, and there's a computer screen. Each individual computer is a node in the cluster. So a node is equal to a computer. It is a computer. It's I use the words interchangeably. I'll probably be using node more often than computer going forward. Does that make sense? And Arno points out that the pre-recorded talk a bit later today on HPC architecture will help to clarify what we mean by universal computer. So the final thing that makes that makes the difference between a local cluster and a high-performance computer is the network interconnect. And as I said earlier, it's the blue thing here, just to remind you. The network interconnect dictates how quickly your individual nodes or the individual computers within your cluster talk to one another. And I know for a fact that on this picture, the network interconnect is a 1 gigabit interconnect, which is really good. I think you can buy one for about 50 quid, 50 pounds, which is probably about $60, $65 US dollars. But what was I saying? Yeah, so the network interconnect is a decent one on that picture that I showed. However, in comparison, it is not strong enough to be useful for a high-performance computer. In a high-performance computer, the speed at which your nodes can communicate needs to be as close as possible to the speed of light. And to give you an idea, the faster the communication time is, the more a group of individual nodes will act like a unit and will start to act like a single computer. To give you an idea, I mentioned the picture above has a 1 gigabit per second interconnect. For ARCHER2, the internode communication speed is 25 gigabytes per second. So is that 4 times faster? Because I think bit to byte is 8. So yeah. So much faster. I heard there were a couple of questions. I'll just check. What limits the size of our HPC system? That's a good question. Quite often, yes. Arno, did you want?
Sorry, go ahead. I can comment, but go ahead.
Did someone?
Okay, since I can't hear you, Julian, I think you're broken up. So yeah, I'll comment. Yeah, I mean, there's a slightly facetious answer that I gave to say money is the only limit. It's not. I mean, not. There's some truth in that because the machines like ARCHER2, which are really at the highest performance end, especially when it comes to the interconnect, the way they've been designed is they've been designed, by Cray or HPE Cray now, in such a modular fashion to be able to scale up like incredibly, because basically what they do is they have a design whereby the topology of the way that you connect nodes, and this is where we get back to your earlier question about nodes, the way that the nodes, the way that when it comes down to it, all the processors in this computer are connected, is done in such a way to make sure that the rate at which the performance of the interconnect in terms of bandwidth and latency, that way that degrades as your machine gets bigger and bigger, is very, very slow. So in other words, the idea is that they design your systems in such a modular way that you could buy one single cabinet, but if you have a lot of money, you could buy 100 cabinets, and you might not be able, you'll need lots of electricity to power it, but the limits are, well, store, how much space can you accommodate, physical space, electricity supply is a big limiter in practice sometimes. Then really the limit on the performance is, well, adding more processors isn't going to make any of the individual processors go slower. The real limit is how fast can you use, assuming you want to use the bigger machine all at once for the same application running. The idea would be, can you use all of those processors as large as at the same time? What's the limit to being able to use an increasingly larger HPC machine with all using the same fraction of it at any given time? The answer to that is the interconnect, really, because it's as we'll see later, it's the processor being able to talk to each other, which in a lot of cases is key. I don't know if that answers some of your question.
Yeah, it does. And I don't want to sort of take over, but I guess perhaps in sort of very simple terms, if you have a theoretical compute for an HPC setup, what would be the actual compute versus the theoretical? What's the sort of the, what's the, I mean, is it literally close to 100%?
Well, the quantifying the performance of a computer is always a thing where there's quite a bit of controversy around how you should quantify that, because you have a metric that's often used is the floating points, number of floating point operations per second, the flops. So that's where the whole terminology of petaflop, exaflop, etc. comes from. And the question is, how do you assess that? Well, you have maybe a theoretical ability of, if you simply take the fact that each individual processor that you've installed has a certain throughput, and then if you just say, well, I've got 10,000 processors, so it's 10,000 times the number of flops each processor can do. Well, yeah, if they were each whirring away completely independently, that's true, but that very few applications do that. In other words, there's some, they'll need to communicate, etc., etc. So the way that this is measured is by running a benchmark. It's somewhat controversial, because it's a kind of benchmark that actually, to some extent, does do this, and therefore makes the process that makes the flop performance of machines look very good. So there's theoretical in terms of very, very theoretical, which is the processor's individual performance timed by how many of them you have. But in reality, when you run real relevant scientific code, it's limited by the communications. It's also limited by memory, because typically you have some kind of data. Even if it's not massive amount of data, it's still data structures in your application. Those need to be stored in memory somewhere and then fetched to be operated on. So there's some memory bandwidth and latency that comes into the equation of the real performance as well. So you've got theoretical, and then you've got what you measure, but how you measure it depends on what you run. So what the answer you get depends on what you run on it.
That helps, thanks.
Thanks very much for the intervention, Arno. I hope you can hear me better now. I've plugged my laptop in. Yeah, cool. Right. So now that we've discussed a bit about what makes a HPC system versus a normal computer cluster versus a computer, I wanted to very briefly give a really, really quick overview of the ARCHER2 system. So it'll be quite brief, because I will be going through this in more detail after the break. But roughly speaking, the way that ARCHER2 looks is the following. What does a HPC system look like? Well, the first thing you do to get onto a HPC system, you can't just physically go there and log in. Well, you can, but usually there's so many users that if we were to do that, you'd probably be queuing behind 1,000 people to get to the single laptop where you can log in, or one of the single laptops. So often what you tend to do instead is SSH into the system, which is just remotely connect into the system to run your jobs. When you remotely connect to the system, you are on one of the login, and then from that login node, quite often you are able to submit jobs to the compute nodes, each node being an individual computer, or be thought of as an individual computer within the cluster. You can submit jobs to a compute node to have your jobs run on these compute nodes. Now you can, for certain systems, you're able to get straight to log in straight into the compute nodes. This is not the case for ARCHER2. Again, we'll get into, like, this is a very, very quick overview. We'll get into much more depth after the break. And to this section, I wanted to talk about who uses HPC. Like, why do we have these large supercomputers for people to use? Why are we spending, I mean, Arno's answer of money is entirely correct of what is a high performance computer. It is why spending millions of pounds building these supercomputers. And from a scientific point of view, and we're taking a very scientific approach to this because we run mainly scientific supercomputers, or supercomputers aimed and targeted at scientific community. There's a number of people who use these. Traditionally, material scientists and solid-state physicists run many simulations. So these are codes like, you might have heard of VASP, perhaps, that do they do quantum chemistry. Computational chemistry, likewise, use very similar codes as the ones above. There's biomolecular simulations. There were a number of people during the introductions who mentioned they were performing molecular dynamics. They fall under the biomolecular simulation category, so using codes like GROMACS, NAMD, LAMMPS, all of those for biomolecular simulations make sense. Particle physicists, there are a number of particle physics simulations that happen. Quantum physics simulations also happening. Environmental modeling is a really, really large subgroup of at least ARCHER2 users. And for instance, I don't know if many of you saw in the news, but there was a volcano that erupted in Iceland. I think it was Friday evening. And over the weekend, some of the people working on ARCHER2 were contacted by some researchers into lava flow who asked for a special amount of compute time in order to simulate the lava flow and see where it was going to flow from the volcano. So that sort of thing definitely happened on ARCHER2. So weather and climate is also done, geoscience, oceanography, and loads of engineering. There's a lot of civil engineering that's now done by simulation before going into labs. And that's true of many other forms of as well. There's loads of modeling of large plants, lots of what's the word I'm looking for? Fluid dynamics to see how air will flow around a plane to make sure that you get the right lift. For anyone who's into race driving, Formula One has huge amounts of money going into modeling of aerodynamics around a Formula One car. So loads of uses of HPC. Now, for less scientific uses, there's definitely going to be things like code breaking. There's going to be security. There's going to be, we're going to delve too much into those ones because they're not a field that we're necessarily as up to date on. So with this, you'll have seen PC platforms do try to cater to computational needs. And one of the interesting things about computing is that it's sort of been a feedback loop of as high-performance computers have gotten better, people developing codes that are often run on high-performance computers develop their code specifically for certain architectures of high-performance computers. So, for instance, Chromax has recently spent a lot of time making sure that they have really good GPU performance, because a lot of high-performance computers have been going in a much more GPU route, graphical processor unit route, rather than your traditional CPU route. And as that's happened, there's been more and more HPC systems that have started to really incorporate GPUs. And there's kind of that loop of the science performed on HPC systems evolves to fit as well as possible on that HPC system. But at the same time, the HPC systems have been evolving to make it as easy for the science run on them to run on them. And that's been an evolution to see. So just trying to see. HPC platforms have the problems except for, yep, I've said that. And yeah, so that finishes a very, very brief overview of high-performance computing. And that, I believe, is nearly the end of our very first session, because I think it's a break after this, unless I'm very much mistaken.
We've got
Maybe I am very much
actually logged on. Yeah, we're going to try and get people logged on to the extent that they've not yet managed, I think. Maybe we should do a hands-on.
Brilliant. I was going to talk about that.
Okay, cool.
Yeah,
it might be, sorry,
that's a very good idea.
It might be worth disabling your video to slightly improve your audio. Thanks.
Sure, I'll try that and let me know if the audio is terrible. Has it been bad? Cool. As Arno suggested, could I ask everyone who's currently listening to put your hands up, please, on Collaborate? Cool, and keep your hands up. Right. Oh, I'll put my hand up as well. That's a good idea. Now, anyone who has connected onto ARCHER2 and has managed to log in, please put your hand down. Okay, so there's some of you, but definitely not all of you. In which case, those of you who have not yet connected onto ARCHER2, have you already applied for an account in SAFE? If you have already applied for an ARCHER2 account in SAFE, please put your hand down. Okay. Cool. So that really helps me to gauge what level of depth I should go into. So for those of you who have not yet gotten an account in SAFE, you will need to go onto the SAFE website, which you can find here. If you don't have a SAFE account, you'll need to go through the form in order to get a SAFE account. I won't be able to show you that now because I've already got an account here. But once you've got that, you will need to go on login accounts, request login accounts, and then choose for this, we will be using account TA017. Could someone put that in the chat, please? TA017, you'll see it's hands-on introduction to HPC for life scientists. Just click on that, click next. You only have one option, so click next. And then here you will request a username, blah one, and you will need to upload an SSH key. I'll talk a bit more about that in a sec. You'll also need to read the terms and conditions and then agree to the terms and conditions. The terms and conditions can be found here. There's a link to them. And then you can click the box, click request, and then you'll have an account requested. Now, I won't be requesting a new account because I've already got one. So quickly check, yeah. I've already got an account. Let me see. So Once you have your account, you will need to log into that account. My account is inventively named TA017JS. The first time you log into your account, you will be asked, you will need two things set up. The first one is you will need an SSH key setup, which I'm more than happy to explain how to do that if anyone wants me to. And you will need your temporary password. Your temporary password you will be able to view by clicking on View Login Account Password. I'm not going to click on that because I don't want you to see my password, and it would be a silly idea to do. The SSH key, I'm actually more than happy to describe how to set one of those up. A moment while I get my shell ready. And let me share the correct screen. That's the one. Cool. Cool. Is this large enough for everyone?
Yep.
Cool, perfect. So to generate an SSH key, what you should run is, and this is all on the ARCHER2 documentation page. So I'll actually put a link to this. It is in best practice, connecting to ARCHER2. I'll put a link to the things that I'm currently using. These are the connection instructions for ARCHER2. To generate a key is SSH keygen minus T, you're defining the type of key, and we want an RSA key. And then minus C, we want a comment. This will be intro HPC test. Cool. Then once you've typed that into your shell, you press enter, and it'll ask you, where do you want to save your key? In this case, it's telling me, do you want to save it in my home directory, in .sh/idrsa? Well, no, actually I don't, because that's a key that I use for other things, and I don't want to have to lose that. But if this is your first SSH key, you don't need to do what I'm doing now. Intro HPC. There we go. It asks for a passphrase. There we go. It didn't match because I can't type to save my life. There we go. Now it has generated my key, and you'll get this information. Let's clear that. And if I go into my .ssh folder and click ls, you will see that I now have ID intro to HPC and ID intro to HPC.pub. So once I've got my SSH key, if I'd been clever and set up my SSH key before setting up my new account, I would have been able to just add it as is. However, because I didn't upload my SSH key when setting up my account, I mean, let's pretend that this doesn't exist for now. I can add it in my account by clicking Add Credentials. I want to add an SSH public key, and then I can choose File. Now on Windows and Linux, I think that the command for toggling between hidden folders is Control-H. So see, there's many less folders when I press this than when I press this. And then I want to find the .ssh folder. There we go. And I want to upload
just so you know, Julian, we cannot see the window.
Oh, it's not showing the thing. Oh, yeah, of course. Sorry. Do you want me to? I can restart the process by sharing my entire screen. I apologize to everyone for the tunnel that you are about to see. Where was it? Here we go. Let's go back. Let's go back. If I press add credentials, I want to add an SSH key. I can choose. Now you should be able to see the pop-up. Is that correct? Yes? I'm hoping those are yeses. You can't see
Finally,
because it's not sharing.
Screen.
Can't see anything now.
Cool. Let's try that again. There we go. There's the tunnel. And there's the pop-up. We got to that page before. If you click Choose File, you can press Control-H to see many less folders, Control-H to see even more folders, which includes all of the hidden folders. I'm interested in the .ssh folder, so I'll just type it there. I'm not interested in that one. And then I want to upload the public part of the key. So in ID intro hpc.pub, I can just click on that and then click Add, and it'll get added pretty much instantly. And if you look, this second key has intro HPC test as its words. Right, I will now go off of sharing because I'm going to be, taking care of what's being shared appropriately can be a bit tricky at times. Yep, cool, that's perfect. So once I've uploaded my key, I can then log in or try to log in to ARCHER2. The way to do this is by running the command SSH -i, I think it's lowercase. We'll see in a sec. .ssh command. You should also have an email confirming that your key's been added to ARCHER2, Arno points out. It also nowadays gets added pretty much instantaneously. SSH -i .ssh ID intro with lowercase, intro HPC. So I'm saying SSH using this key, and I want to SSH to TA017JS. That's the name of, that's my account name, at login.archer2.ac.uk. I click that. Hopefully it's not too unhappy. Did I get, yeah. Can't ping to ARCHER2. Ah, there we go. Sorry, one quick thing while I check that I'm not being, yeah. I'll check with my colleagues. Arno and Holly, are you both able to log in?
Let me just check that for you.
I think I know what the issue might be. There we go, yeah. So there's currently a problem with one of the two login nodes for ARCHER2, so we need to specify the other login node, which isn't currently being rebooted, which is why... Oh, no, they're both fine. So I do not know what went wrong. It seems happy again, cool. That was just a temporary glitch. So now it's gonna ask for my password, and the password I need to give it is the temporary password in safe. So I'm just going to copy that and paste. Is it the wrong? Copy and paste. I'll ask for a new password. Cool. go. I thought I'd reset it, but I clearly had forgotten to click something. There we go. Copy, and let's not paste it into here, but instead do this. Paste. Why are you unhappy?
Julian,
Yeah.
can you hear me?
Yeah.
Okay, so I'm having the same problem on ARCHER2, and I was logged. I was disconnected, and now it's just saying permission denied. So I think it's an ARCHER problem.
Oh, cool. Thank you very much. I'll try on the other login node to see if that's any better.
I didn't try that.
There we go. So thank you very much for pointing out that there's an ARCHER2 problem. Because I'm giving a course I hadn't noticed.
Yeah,
so you'll
that
need to
works.
SSH to login to archer2.ac.uk, and that should work.
And thank you for telling me about the second login.
We try to keep it hidden, so usually you should always log in to login.archer2.ac.uk. But it's just in this special case, because it's a course, we're fine to do it. So, what are we on? Fifth time? Fifth time lucky. If you go on login2.archer2.ac.uk, you can then change your password. And because this is a temporary password, I am now asked to change my password. I am told you need to change your password. And then it says enter your password. And this is a bit confusing to people. The password that you now need to enter is your temporary password again. So you enter your temporary password again. I just pasted it in, and now it's asking for my new password. So my new password is my new password's been typed. Now at this point, I'm going to quickly change so that you can see my entire screen again. Sorry about this having to go back and forth and it taking like 2 seconds every time. I'm kind of doing this on the fly. There we go. Hopefully that's shared. Entire screen, allow. And now, why are you unhappy? Sorry. There we go. Sorry, let me quickly go off that. So now that I've entered my password and it's happy that I've entered my password, it's asking me for my SSH key, and it's asking me specifically for the passphrase that I put for intro HPC test. I enter that, and now hopefully, though I did take a bit of time, there we go, hopefully we can now access ARCHER2. And as you can see, I am now on ARCHER2 in my home directory. I'll stop sharing my screen. So at this point, has anyone... Yeah, so Luciana, I might need to approve your account, or one of Arno and or Holly can approve your account. I'll check real quick. And hopefully I'm not sharing my screen at the moment. Yeah. Oh, you can log in and you're logged in. Brilliant. So out of everyone who didn't have an ARCHER2 account, please put your hands up if you still don't have an ARCHER2 account. I'm going to lower Rui's hand in case he maybe didn't post that since before. But of the people still here, how many of you have not yet logged into ARCHER2? Please put your hands up. So Ludovico, and I'm going to quickly share that one. Ludovico, and I've not had yet a safe request telling me that you ask for a new account. It can usually take about 2 to 5 minutes for me to get that email, but until I get that email, I'm not going to be able to do this. You have the safe account. So if you follow the steps that I just described or the steps that I posted online, you should be able to log in. Okay. And if not, I'm more than happy to stay in the break and try to help you find out what the issue is. For everyone else, very quickly, I wanted to, so we've connected to ARCHER2. One thing I wanted to talk about is the ARCHER2 password policy. Cool. That might be a case of either you're entering the wrong passphrase or, I mean, usually that means that you're entering the wrong passphrase. But again, I'm more than happy to talk about this during the break, if that works. So the ARCHER2 password policy, you can find more information about it on this link. But basically, the password policy is that you must have a password which is 18 characters in length. And then for every complication that you add to your password, you can reduce it by 2 characters. So the first complication is if you have lowercase letters, you can reduce it from 18 to 16. So if you have a password which is entirely lowercase letters, you can have a 16-character password. The second one is if you have uppercase letters, you can reduce it by a further 2 units, meaning that you can have a 14-character password if you have both uppercases and lowercases. The other 2 criteria, each of which reduces it by 2 characters, is using numerical characters and punctuation. So if you have a password that has uppercase, lowercase, numbers, and exclamation marks, for instance, or exclamation marks, pound signs, dollar signs, percent signs, at symbols, whatever, you can have a password which is 10 characters long. If you have one which has punctuations, numbers, and only lower cases, then it would need to be 12 characters long, etc., etc., etc. So with that, just to make sure that you've understood the ARCHER2 password policy, oh, there's one more thing actually about the ARCHER2 password policy is that we run any password that is suggested through a dictionary check. So you can't have a single word that's in the dictionary as your password, because those are a bit too easy to crack. So having said that, we have here 4 passwords, 4 potential passwords. Out of these 4 passwords, please put your hands up if you feel that password number 1, my password, is a good password. Alternatively, no one's put their hands up, which is probably a good, thing because it's a terrible password. What about rainbow llama jumping? Would that be a valid ARCHER2 password according to the password policy? Please put your hands up if you think that would work for ARCHER2. Yeah, so Luciana thinks it will. Holly does as well. Miguel does as well. And indeed, this would be a valid ARCHER2 password, because if you count the number of characters, there are 18 lowercase letters, which means that it is of the appropriate length. And even though it only has 1 complication to it, it's only got lowercase letters, it's still absolutely fine and a valid ARCHER2 password. And indeed, quite often, the easiest passwords to use, the ones that are more easy for you to remember, but hardest for a computer to crack, are passwords that have many words in a line. So something like rainbow llama jumping or horse battery staple are both quite good passwords. That we'll get on to horse battery staple in a sec. What about password number 3? Uppercase A, exclamation mark, 94, lowercase UFS, KL, $, question mark. Yep. So interestingly enough, more of you think that this is an appropriate ARCHER2 password, and indeed it is. However, going back to what I was saying about putting together random words to make your password, I don't know about everyone here, but I find rainbow llama jumping way, way, way more easy to remember than uppercase A exclamation mark 94UFSKL $? Both, as far as the ARCHER2 policy goes, are equally sensible passwords, and both would be allowed. Now for password number 4, please put your hands up if you think that password number 4 would make a good password on ARCHER2. So it fits, a few of you say yes, and it fits all of the criteria in the sense of it's the right length of characters, and it's at least 18 characters, and it's all lowercase. However, this password comes from a relatively famous webcomic, which is a very good webcomic to read generally because it's, well, this particular one is worth a read generally because it really discusses password strength. I've put the link in the description. But in this webcomic, they describe exactly the things that I described of Troubadour is a quite complex password for a computer to crack and has about 28 bits of entropy, which is roughly a measure of how quickly a computer can break it. And they make the point that Troubadour, which is a super hard, or Troubadour and 3, which has uppercase T, a 0, a 4, a special character, things like that, is a very hard password for a human to remember, but actually quite easy for a computer to crack. Whereas if you take 4 random words, or 3 random words, or a number of random words and put them together, it becomes incredibly hard for a computer to crack. But for humans, it's much more easy to remember. And if we look at the solutions, you'll see that, yeah, my password is a terrible password. Well done, everyone, for not putting your hands up. 2 and 3 are good passwords, and 4, while it does meet the criteria, because it's a password that's out in the public domain and is especially out in the public domain with people who use HPC a lot, it suddenly isn't as good a password anymore. So we've discussed SSH keys and how to log into Archer. So I just wanted to take briefly 1 or 2 minutes to talk about transferring data onto or off of ARCHER2. We have 3 main ways of transferring data. You can either use the SSH copy, SCP command, to copy things from your local directory, from your local system onto ARCHER2, or off of ARCHER2 onto your local system. There is rsync, which is another file transfer method, which will synchronize a file between 2 systems. The advantage of rsync over SSH copy, or over SCP, is that you can do partial transfers with rsync. So if for whatever reason your connection gets lost midway through your transfer, with SCP, you'll need to start back from the very start, whereas with rsync, you should be able to continue from wherever it left off. Both of those are good for transferring files of order megabytes to gigabytes. And then we've also got access to Globus Online for much larger amounts of data, such as terabytes worth of data. Someone's asked, what about SFTP? I'm not sure. I don't know the answer to that. I don't, off the top of my head, I don't think we have it, but maybe Holly and Arno can tell me I'm wrong. Otherwise, I'll ask some colleagues during the break to make sure, to give you an answer after the break, if that's okay. Holly and Arno are not telling me that.
SFTP should be fine. Mm-hmm.
SFTP should be fine. There we go.
It's listed underneath the link there.
Oh, cool. Cool. And so with that, now we do actually come to the break. And we'll now have a 20-minute comfort break for everyone to make themselves a cup of tea or coffee, I guess, whichever's, or just water, whichever you're more interested in. And we will reconvene in 20 minutes. If anyone has still not logged into ARCHER2 and would like some help getting logged into ARCHER2, Holly, Arno, and I will stay around to try to help you make sure that you've got access to ARCHER2 for when you come back. And the other thing I wanted to mention is that after the break, the lesson is a pre-recorded lecture. So you can find the slides and the pre-recorded presentation here. I'll put the link in the chat. Arno, Holly, and I will be here to answer any questions that you might have. But the idea is for you to watch this at your own pace over the break. And then we will be doing some exercises on ARCHER2 to really emphasize the information that you hopefully will have learned during the pre-recorded lecture. So with that, I hope that you all have a good break, and we will see you in about 18 minutes.
So it's 20 past now, and some people may have finished already with the pre-recorded lecture on HPC architectures. If you have, feel free to ask any questions. We'll start in a bit on the when student gets back. We'll start on the next session, which is a bit more practical, getting stuck into to seeing how to make software modules available in Archer. Just to motivate maybe a little bit why the HPC architecture is kind of lecture, why we're telling you these things. Questions, why do you care? I mean, what we're trying to do in the course as a whole is really cover both sides of hardware and software and the kind of the usage, everything you're actually trying to do with these machines, and the software you care about is always at the intersection of these two things. So by giving you a better sense of the hardware, we're trying to also I can hear someone. Is it Julian or? Yeah, I'm just gonna mute you, Julian. Sorry. Yeah. Okay. Thanks. Yeah. So so a lot of the things we're telling you is we're kind of circling around a couple of times. So some of the things we're telling you is kind of we're telling you the same thing in different levels of detail a couple of times over. So we've mentioned already in the HPC architectures lecture, we've mentioned MPI and thread, but we'll come back to that. We've mentioned processors and cores, but we'll come back to that in more detail. So it's a bit like we're circling around several times different levels of overview. But one of the key things about the HPC architectures is this idea of compute and data, of memory and processors and how they're connected. And it's a whole hierarchy of where these things are located that has a big impact on how we run things. Okay, I can see Julian is messing around, so I think I can hand over it now and let you pick things up. Oh no, it's Louis Joao. I think you're sharing. Well, if there are no questions and Julian's not starting yet, I can address one of the previous questions, which was, so I think one of Richard's question was, what's the difference between a node and a computer? I mean, a node is a node in a network. A node is just, I guess, a node is a computer that, a node is a unit. I mean, you could say the computer is a big machine consisting, ARCHER2 is a computer. But if we're talking about looking at starting from small and building things up in the way that Julian is pointing out, if you have a cluster that's built up of these individual units, each of which you start off by calling a computer, then they just play the role of nodes in a network, I guess, nodes in a topology of connections. Yeah. Okay. Julian's back. So if you want to take over next session.
Great. Thank you very much, Arno. So next session, next session, we will be mainly, this will be predominantly a practical session. Let me check, that's the wrong one, so it should be that one. Yeah, that's right. It should be predominantly a practical session, and in this session, I want to give everyone here an overview of the ARCHER2 system and talk a bit about modules, how they work, how you can use them, and how they can make your life a lot easier. Most everything that I'm going to be talking about in here is very specific to ARCHER2, but you'll see a lot of similarities with other HPC systems around the world. So to start off with, you've seen this picture before, but now that everyone, or hopefully everyone's been able to log into ARCHER2, we can talk a bit more about the ARCHER2 architecture. So by now, hopefully everyone's logged into ARCHER2, and you should be on a login node that says your username and then I will actually just share my terminal, makes it easier. I'll share my entire screen. My screen sharing? My screen is sharing. Cool. So you should be in a terminal. Hopefully, if you've logged into ARCHER2, you'll see all of this lovely ASCII art telling you that you're on ARCHER2. There should be some descriptions of the system, and then you should be on a page that says your username at UAN01 if you're on login node 1, or UAN02 if you're on login node 2. So at the moment, we're on the login nodes, and all users have two spaces that they can access from the login node. There is the /home space, which you all start up. We all start off on. So if I do present working directory, it says that at the moment I am in /home/TA017/TA017/ my username. We are everyone who is part of the TA017 budget will have a similarly named folder. And if I go one directory up and press ls, here are all of the usernames of everyone who's in this group. Let's go back to home. Now, on top of that, all ARCHER2 users have a workspace as well. So there's a home directory that everyone has, and there is a work directory in /work/your budget code. So in this case, TA017/your budget code again, /your username. The reason why my username is TA017JS is because after a while you end up with so many usernames that just putting the budget code and then your initials is quicker when coming up with new names. So both spaces are empty at the moment because this is a brand new directory and I've not done any work in under this particular budget. So there's not much exciting to show. However, the two spaces are not the same. So if I were to make a file, I tend to use Vim. I know that there are people who prefer Emacs. Emacs is definitely on there. There's also some people who like to use Nano. Nano's on there as well, but I'm definitely VI. If I create a file in work, that file does not appear in home. No file in home. And the reason for this is because your home and your works on ARCHER2 are separate. There's a couple of reasons why this is the case, but one of the big reasons is the following. The compute nodes can only see your workspace, meaning anything that you keep or store in your home directory cannot be seen by the compute nodes. So usually your home directory is going to be a lot smaller, as in have a lot less space for you to use than your work directory. So why have a home directory if the compute nodes are going to only see work? Well, the reason for the home directory is the home directory is smaller, but it is backed up. The work directory is not backed up. So if something terrible were to happen, we are very open and honest about the fact that anything in your /work directory is lost. If tomorrow, for whatever reason, Edinburgh was wiped from the map, your work directory would be lost. Anything you had saved in your home directory would still be available. We have, depending on the scale of how bad the rest of the UK and/or world are doing, this might not be the case. But there are emergency backups in place for the home directory. Now, I'd quickly like to take a second to emphasize the point. They are emergency recovery backups. They are only there for if some really bad thing happens to the entire system. This does not mean that if you accidentally deleted a mega important file in your home directory, we would be able to do anything about it, because while it's very sad that you deleted this super important file, it's not deemed a an emergency, if you understand what I mean. So that's the distinction between the home and the work disk. Now, at the moment, we are on the login node. There are ways to log into the compute nodes, and we might see a bit more about that at a later point in this course. But for the moment, we're predominantly on the login node, and from this login node, we should be able to write scripts that should be able to launch jobs onto the work nodes. Now, ARCHER2 has a large number of compute nodes. It currently has 1,024, and there will eventually be 5,848 compute nodes. And each node has 128 cores, which means that there are a total of around 750,000 compute cores on ARCHER2. I've kind of discussed already the memory, but the compute nodes usually have 256 gigabytes of memory, and there will be around around 300 nodes with more than 512 memory for people who want to run higher memory jobs. And all compute nodes are linked together using the high-performance Cray slingshot interconnect. That's the network connection between all of the nodes that I mentioned in the previous talk. For anyone who's really interested in the hardware, you can find all of the information about the hardware here. You can also find that information on the ARCHER2 website at archer2.ac.uk. Archer2.ac.uk. I can type almost. 2.ac.uk. Or if you just Google ARCHER2, there we go. It probably needs the www. If you go on About, it has all of the information about the hardware on ARCHER2. Cool. So I've mentioned two different types of storage. At the moment, we've got home space. We've also got the workspace, which I've discussed. And the last one that we have is, it's not currently available, but there will be a small amount of solid state, I think about 1 petabyte of solid state, for people whose work really requires quick reading and writing of information to the hard drives. So for anyone who's quite new to using shell, a very important command, and you'll have seen me use it already, is let's say that I'm in my work space. If I'm here, a very quick way to so I've just moved that directory to, or moved that file to say this is work, so that whenever I ls, you know that I'm in my workspace rather than my home space. A very quick way to return home is to do cd tilde. And now if I do present working directory, I am in /home, whereas before I was in /work. Yeah. So that's a useful trick. Now, there's no subprojects here, but for some projects, there are subprojects. Let's talk a bit more about, I'm going to focus here on the home directory, but be aware that the work directory is set up in exactly the same way. So everything I'm going to say now, until I mention otherwise, is also true of the workspace. So I've got my own directory. If I do cd up, I've already mentioned you can see all of the other users, including Arno, Holly will be here as well, and one in particular that I want to see is this one, shared. Shared is not a user. Shared is a shared directory within this budget group. So if you go in home TA017 TA017/shared, and you can place things here that anyone from this budget can see. So now anyone who has a TA017 account should be able to run cat TA017, TA017 shared. Hey everyone, and see what I just wrote. I should ask an exclamation mark. Sorry. All right. Here we go. So anyone can run this command, and you should be able to see that file. I'm just going to put it in chat real quick. Sorry about the tunnel. Wrong chat. There we go. And now let's move away from the tunnel. Sorry about the tunnel, everyone. So anyone can see this shared directory, but only people within the TA017 budget are able to see this directory. If I were to log in with a different directory, I wouldn't be able to see, with a different account, I wouldn't be able to see this. And indeed, I'm happy to very quickly there we go. So I am now in a different account. And if I do present working directory, I'm in account D118JS. If I were to try running that same command, I am not allowed to. I get a permission denied because I am not part of the TA017 budget code. So how do you share something with someone who's outside of your budget code? Well, if you go one higher, you'll notice that there's a TA017 group, and then there's also a shared file here. And if I were to cp TA017 shared, hey everyone, and put it into this shared file instead. So cat hey everyone, here it is. Then from my other account, from this account, I should be able to see it. And yet you can see that even from my other account, I'm now able to see this. So those are the shared directories. They're kind of useful. They're very useful for sharing information within a group and with other people on ARCHER2. And just as a quick, just to force the point, if I go into the work directory, there's a shared in TA017, and there's also another shared in TA017/TA017. So other quick things to mention. I think I did not mention that the home directory has a total of 1 petabyte of usable space. The work directory has 14.5 petabytes, so nearly 15 times more than the home directory, and is set up in much similar way. As I've mentioned, the compute nodes cannot see your home directory. So if you get an error message saying, I couldn't find the file, make sure as a first step that the file that you wanted to submit to the compute nodes is in work and not in home. I've talked about how to share data. Yeah, so at this point, I think it's time to start about the ARCHER2 module system. I thought I had some information, a bit more information about the soon to be available SSD drives, but yeah, apparently not. So moving on to modules. What are modules as well? So ARCHER2 uses a module system, which provides access to users and helps users get different, what's the word I'm looking for? Get different software loaded up and ready to use as and when they need them. So you can see what modules are loaded when you first log into ARCHER2 by running module list. And that tells you all of the modules that you have currently loaded when you first log into ARCHER2. You're in the Cray programming environment. We'll probably talk a bit more about that when we talk about compilers, so I won't stress this too much. And there's a number of things that are already available. Now, how do you find out what other modules are available? You can type module avail and press enter, and it'll load up or it won't load up, but it'll show you a list of all of the modules that are available on ARCHER2. So there's things like TensorFlow, there's NetCDF. The first few modules that are shown are modules that have been installed by the ARCHER2 CSE team, the support team that Holly and I are part of, to try to make life for users. So the first few are mainly libraries, but then you get to some shared packages. So for instance, there's a version of GROMACS here. There's GROMACS with Plumed, LAMMPS, NAMD, VASP, which I mentioned before, Quantum Espresso, CP2K, and a number of other codes. Then we also have software that's provided by Cray. So we have a contract with Cray, who are the people who put together the supercomputer, or at least ARCHER2. And part of the contract is that they provide some of the software as well as the hardware to make sure that ARCHER2 performs as well as possible. And the next couple of libraries are things that I'm not going to get too much into because they're provided by Cray and are useful if you're wanting to get really much deeper into programming and compiling than we're trying to cover in this course. I'm happy to answer questions, as are Arno and Holly, if you have specific questions about any packages, but I'm just not going to go too much into the Cray packages. Cool. Let's go back here. There we go. So okay, I said there was a GROMACS module, but how can you find out more about the GROMACS module? Well, if you're looking for a specific module, one good thing you can do is module avail and then say GROMACS with the asterisks are wildcards. So I'm saying if there's anything before or after this, feel free to include it. I just care for anything that has the word GROMACS in it. And then it shows me that there are two GROMACS modules. There's 2020.3 and 2020.4 with Plumed. I say it's with Plumed, but maybe I'm not too sure what 2020.4 plus Plumed mean. How can I find out more? I can run module, I believe it's show, but it might be, it is show. GROMACS 2020.4 with Plumed. And I get not very much information, but it's telling me the path. Module help. There we go. Module help, and then the name of the module. And if the module has been written well, it'll give you some information about the module. So here it tells you this is using GROMACS 2020.4. And this module sets up environments to allow you to use GROMACS 2020.3. That should really be changed. And I should, yeah. But yeah, so it gives you some information, even though in this case it's wrong. I will change that during the break. And it tells you what you're using and how to use it. So how do you, let's do 2020.3 because that one will be correct. And then it tells you right at the end, I've sort of included a thing saying, well, how do you use the module? You use it by running gmx mpi and gmx mpi_d. So then the next question is, at the moment, if I wanted to use this, well, I don't have a gmx mpi. It's not working. So how do I use the module? How do I load up the module? Well, the answer is in the question I asked. You run module load GROMACS. And if you just type that, it will work. If I then run module list, I have, as my 16th module, GROMACS. And it says it's GROMACS 2020.3, and then in brackets, default. Because I didn't specify which version of GROMACS I wanted, it gave me the default version, which I'm fine with because they're new. I mean, I don't really need Plumed right now. And now if I look for it, I now have GMX MPI, double precision, and GMX serial. Serial being the serial version. So I now have these executables and I'm able to run them. It's not going to be happy, but yeah. So anyone who's used GROMACS before, you'll know that this is what you get when you don't use it properly, or one of the things you can get. Okay, but now let's pretend that instead of wanting this version of GROMACS, I wanted the other one. How can I change that? The easiest way to do this is probably to run module switch GROMACS with the other version of GROMACS. And what that will have done is it will have unloaded GROMACS 2020.3 and loaded up GROMACS 2020.4 with plumed. And if I do module list now, you'll see that I no longer have 2020.3, but I have 2020.4 with plumed. But let's pretend for whatever reason that I don't really want GROMACS. I can easily unload the module by running module unload GROMACS. Module list, and now I don't have GROMACS anymore. So there we go. That's a very brief overview of modules on ARCHER2. The main thing to keep in mind about modules is it's a way of making it easier to not have everything loaded up at once. It allows you to really plug in the bits of code and program that you need in order to run your simulations or run your software properly. I'll just check I've not forgotten anything. We've talked about module list. Oh, that's a very important thing to, I'm getting some messages. Sorry, I will try to, I'm trying to protect you from the evil tunnel vision. There we go, that works. So what's the difference between GROMACS single and double precision? That's a very good question. The difference between GROMACS single versus double precision is how many decimal points you're interested in, roughly speaking. Oh, Arno's answered the question. So single precision is usually a faster version, as Arno says. You achieve faster performance but less precision. So it's a less accurate answer. Usually in molecular dynamics, you're absolutely fine to use single precision, but some people like double precision. Next question is, how do I locate a specific package if I don't know the name? For instance, if I want to use netcdf tools, but know nothing about netcdf, so the way I would go about this is if I was interested in anything with netcdf, I would run module avail wildcard netcdf and wildcard, and that will output every module that has the text netcdf anywhere in the anywhere in it. So it's output all 4 of these libraries. Cool, brilliant. I'll go back to full screen. So I've talked about which modules are loaded, module list, module purge. I've not talked about this. This is quite a fun one, actually. Please, please, please don't do what I'm about to do. There is a command called module purge, which will remove and delete every module that you've got loaded up. And if I run module purge, hopefully, if we've said it right, it stopped me. Yep. So I don't have any module files currently loaded. See, no modules files currently loaded. However, this the module that deals with module, or that gives you the list of modules available, is one of the preloaded modules, which means that now if I type module avail, oh, it does see it. Oh, we fixed this. This is great fun. Oh, no, it only shows the Cray modules. So you'll see that it shows only the Cray modules, but none of the modules that we, as part of the in-depth team and support team, have made for users. So there's no way for me to load GROMACS, for instance. There's no GROMACS. And just to make absolutely certain, there's no. So at this point, if you ever do this by accident, and I hope all of you didn't do this, by the way, or none of you did this, you will need to exit and log back in. I can remember passwords.
Julian?
Yeah.
It might be worth pointing out at this point. I mean, I know maybe you mentioned earlier, but the reason we're telling you about this, people about this as well, is that this is not necessarily that specific to Archer. The environment modules is a thing that's, you know, whatever HPC system you log into, it's very often used. So being used to these commands is very useful. And I was just going to touch on one other point. the file system, I think you put something in the notes, but it's worth pointing out that, I mean, I don't think we really covered anywhere else in the course because we're focusing mainly on processors and memory, but the file system, in particular the parallel file system that a machine like ARCHER2 has, is also actually one of the distinguishing features of an HPC machine that makes it high performance, because it's a parallel file system in the following way, that there are files instead of being stored, instead of a particular file being stored in one place, especially when it's big, it is cut up into lots of pieces, and those are striped or stored across different disks, and that is all done in order to enable much faster reading and writing in parallel by large-scale software applications. So it's just another distinguishing feature of HPC machines.
Yep. Do modules such as GROMACS need reloading on every login? Asks Peter. Yes, they do. And I'm more than happy to show that. Thanks, by the way, Arno, for that intervention. It's true, I should have maybe mentioned a bit more about that. So I've just relogged into ARCHER2, and if I run module avail, or module list rather, to show the modules I have loaded up, I do not have GROMACS currently loaded up. If I module load GROMACS, because admittedly I didn't have any modules loaded when I last was here, it's now loaded. I exit, I go back in, and module list, it's no longer there. Apart from these 15 modules that all users have as a default when they log in, no other modules are loaded on login. So that's module purge. Do be careful about this. We've talked about what software is available very briefly. There is, so this is very specific to ARCHER2. Some of you may have noticed that there are some software, such as VASP, which is licensed software. And you are able to apply for, if you have a valid license for using some of the licensed software, you are able to, in safe, where is safe? There is safe. That's fine. It's not my password anymore. If you go in safe, you will see that there is a button here for request access to packages, and these are all license packages that we have a central installation of on ARCHER2. So we've got CASTEP, ChemShell, Crystal, the Met Office Unified Model, VASP, and OneTap. You will need to provide us with some form of proof that you will need to provide us with probably a license code or your email address so that we can check with the developers of those software to make sure that you are allowed access to this. But you should be able to get access to the central version. In the meantime, I'm still able to module load VASP. However, I don't have access to any of the VASP code, so I don't know if I try. Yeah, if I try running anything VASPy, it's going to be unhappy and not work. I'm hearing a lot of things in the chat. I'll check if there's anything that I should be answering. When loading modules, you can do this in either work or home directory. Yep. Loading modules you can do wherever you want. You can load modules from the login nodes, you can load modules from the compute nodes, you can load modules from any directory you want. So just to labor a point, I will go in the top directory of ARCHER2, and I can module load GROMACS, module list. Now I have GROMACS, module unload VASP, module list. Now I don't have VASP. All of this information is stored as part of, I'm not quite sure which file it's in, but it is stored in a very local fashion. So modules are mainly linking you to the software that you can use. So they're linking you to the executables that you'll then be able to run, rather than linking you to any physical data, if that makes sense. Right, that's what I wanted to do. So licensed software we've talked about a bit. Loading and switching modules we've talked about. I'm pretty sure this is pretty much it, and licensed software. Now, if you have any problems with any software or any questions about any software, the first place to look for, well, during this course, definitely just send us a message and we'll have a look and try to answer. The next place to look for answers would be the ARCHER2 documentations, which is here. And then if you still can't find the answer to your solution, please feel free to send an email at support@archer2.ac.uk, and then it'll get sent to one of our support team, possibly even Holly or me, and we'll try to help you as best we can. Now, obviously, for this course, you have Arno, Holly, and me here to help you with any questions, so ask us before you send emails, but that option is available to all users, and if you'd rather get someone else to answer your question, you're more than welcome to go that route. Pedro asks, can you change your Bash profile to open modules automatically? I think, yes, you can. Be very careful about that, because we've had many users who've had unexpected problems because they didn't realize they were loading up a module when they thought they weren't. For the last 4 minutes, I'll briefly talk about the ARCHER2 documentations. The ARCHER2 documentations, oh, that's the wrong one, sorry. The ARCHER2 documentations have we've tried to make them really useful. Like, genuinely, please do have a look whenever you need anything. Like, you know, if you're wanting to find out about GROMACS on ARCHER2 and you can actually type, you can find out information on GROMACS, and it tells you the available modules. It has an example script for running on an example Slurm script. Don't worry if you don't know what that means. We'll be talking about that after lunch, as well as some tips and pointers. And at the end, it has a link where if you click on the link, you get sent to a page because the link is wrong. Oh, that's weird. Need to check that. So we try to keep a link which sends you to build instructions, so that if you want to build your own version of any software with special modifications, you can just click on that link and go straight to that. On top of that, we've got a quick start manual for anyone who's just starting on ARCHER2, or anyone who wants to develop code on ARCHER2. We've got, like, this is much more in depth than what we'll be going through in this session, or in this course, but that's available there as well. We've also got frequently asked questions, and then a really good in my opinion, really good best practice guide that covers things like connecting to ARCHER2, data management and transfer, how to run jobs, how to get better performance in I/O. If you don't know what I/O is, don't worry, we will describe that, but it's roughly the speed at which you read, your program will read from hard drive and write to hard drive. And many other things, how to use Python, how to debug code, loads of information like that. And then information about research software, libraries that we keep, and other things. It's a really good, well, I think it's a really good documentation, but then I helped write it, so maybe I'm biased. Right, so with that, I think that takes us to lunch. Before we go to lunch, I wanted to key points. Our ARCHER2 has high-performance login nodes, compute nodes, storage systems, and interconnects. There's a wide range of software available on ARCHER2. I did not mention, but hopefully it was evident that ARCHER2 runs a version of Linux with command line access. Everything I've been typing in my terminal has been command line, but hopefully you all know this, and you can get access to our software through the modules. With that, that takes us to lunch. Lunch is from now until 20 to 2, so for the next 20 minutes. And after lunch, there is a pre-recorded lecture that Arno has prepared to do with queuing systems on HPC machines. And this is much more delving into, now that you're able to move around in your directories and you know about home, you know about work, great, what are the steps to getting to the point where you can run, say, a GROMACS simulation? And Arno will talk about that in general during this pre-recorded lecture. And following that, I will talk specifically on ARCHER2, how does it work on ARCHER2, and how can you do it, with hopefully getting you all to run your first jobs on ARCHER2. At this point, I'll ask what are the questions that everyone has so far, and I will stop sharing my screen because no one likes a tunnel. And otherwise, I think the plan is, and Arno, stop me if this is wrong, but I think the plan is we're more than happy to stay around and chat and hear any questions that anyone has, or even like hear what sort of day you're having or anything like that. We'll probably try to pop away for lunch, but we'll take turns so that there's always someone here who's able to, more than happy to and able to chat to anyone from the course who has anything they want to talk to us about. Otherwise, we'll see you at in about 40 minutes to answer any questions, to answer all of the questions that you might have about batch systems and submitting jobs on supercomputers. And when I say we're here to chat, we genuinely are more than happy to hear about the research you're doing, why you're interested in HPC, but even things like, what you're planning on having for lunch, dinner, or whatever. Hey everyone, please could I see a show of hands for people who are back, please? Right, what I might do is start a quick poll. That way the poll will still be running when new people join. And I'll give people another 2 to 3 minutes. Multiple choice. I need to add 2 choices, which is why the second choice is a bit silly, but there you go. So I'm definitely back. Cool. And before I start and go straight into ARCHER2, or how to run jobs on ARCHER2, does anyone have any questions for Arno about the things that he talked about in his pre-recorded lecture? So one question we have. Yeah, sorry. One question we have in thread is, what's the difference between a NOR, a core, a thread, a socket? So we'll go into a lot more detail for this tomorrow, and there's actually going to be an entire lecture just to explain the difference between these. But very quickly, a node is essentially one of the computers that is a component of a HPC facility. It potentially could run by itself if you wanted to, but usually you don't. A core is a subpart of a processor. So you've got modern processors are broken down into many subparts. Each of those subparts is a core. A thread is can mean one of 2 things, but usually it's associated with running things on using OpenMP. And a socket, I'm probably wrong on this one, but I always assumed. How would you describe a socket, Arno?
I mean, I just stick it to ally the processor to a socket. I just think a processor is a thing that you stick into a socket. It's a chip with one or more cores that you stick into a socket on the motherboard. That's kind of the way to stay sane when you think about this stuff and not get confused by things. And when it comes to CPUs, that's a whole other thing, because it's software. It's historical software terminology in the Linux operating system. Sometimes it uses the word CPU in a way that has changed over time and is now confusing. But cores, sockets, cores and sockets, we can give a straightforward physical interpretation of. Yeah, we'll cover that tomorrow.
Cool, great, thank you very much. And to give one final question, are there any questions that anyone wants to ask Arno about his presentation? Please either write them in the chat, write them in the Etherpad, or I'll put a link to the course material and the Etherpad right now in the chat, or raise your hands, and please do go ahead and ask your questions out loud as well. We're more than happy to hear them. Is that the right link? That looks like that was the right link. That was lucky because that was the wrong page. Cool. And there's the course Etherpad. Right. As there do not seem to be any questions, I guess we'll just carry on and move straight on to the practicals of how to submit jobs on supercomputers, or at least on ARCHER2. Sorry, give me one sec to share my screen. I apologize for the tunnel. Cool. Is it happily sharing? It's happily sharing. Right, so by now, hopefully everyone has access to ARCHER2 and has been able to log into ARCHER2. If this is not the case, please do let us know, and one of Arno and Holly will get in touch to help you. But at this point, a lot of the rest of the practical sessions are dependent on you having access to ARCHER2. So please let us know if that's not the case. So far, we've mainly been talking about where you can store information on ARCHER2, and alluded to the fact that there's many compute nodes and that you can submit jobs onto those compute nodes. Now, Arno in his lecture described the general ideas of schedulers and why they can be useful, namely all of the benefits of that way you can just submit something to the queue and walk away and it'll run whenever it gets to the front of the queue, and also make it easier for multiple users not to ask for the same piece of resource at the same time. Now, ARCHER2 uses the Slurm job scheduler. The Slurm scheduler is I was really happy to find out recently that the name Slurm actually originates from the fake fizzy drink in Futurama, which I find brilliant. It's an acronym. It stands for something. I never remember what it stands for. It stands for Simple Linux Utility for Resource Management. Not particularly useful for you to know, but there you go. And it's a really nifty little scheduler that allows users to do a really large amount of things quite easily, especially once you get your head around it. It's a bit tricky at first, but once you get your head around it, it's a really easy, quick one to understand. And it provides users with a lot of information quite quickly and quite easily. So the very first command to consider is probably the sinfo command. And what the sinfo command does, sinfo, will give you the information of the current Slurm queue. I press that and it tells me, what does it tell me? It tells me the partitions, so which nodes are in which parts. Slurm is built in such a way that you can have different, it's built to not just work for supercomputing clusters, it's also built to work for group clusters and smaller clusters, where maybe you don't have all of the same computers, and parts of your cluster are made up of computer type A, and parts of your cluster are made up of computer type B. Slurm makes it really easy for you to set a group of rules for computers of type A versus a group of rules for computers of type B, and by allowing you to set up partitions. So for this, all of our because all of the nodes are the same, we've only got one partition, which is standard. So you'll see that all of the nodes have partition standard. Availability just tells you, are the nodes up or are they down? And you'll see they're all up at the moment. Time limit here tells you how long a job you can run on these particular nodes. So in this case, you can run 1 day, 0 hours, 0 minutes, 0 seconds. So you can run up to 24 hours or 1 day on any of the nodes here. And that is the max allocation time for most jobs. Here it tells you how many nodes are in this specific section. So you'll see that in the top one, there's 19. The big one here, 945, is where most of the nodes are allocated. And then there's a couple of others in various places, including in reserves and other things like that. Here is the state of the node. That tells you what the nodes are doing. Drain means the nodes are down. There might be an issue with them. Our systems team are probably investigating, or they're just not responding when the scheduler is asking them what they're up to. So drain usually means the nodes are down. Alloc stands for allocated. This means that at the moment, there are 945 nodes on ARCHER2 that are currently doing work. As I said before, there's about 1,000, a bit less than 1,024. I think let's call it 1,000. There's 1,000 total nodes. That means that 94.5% of ARCHER2 is pretty much currently busy. Of late, ARCHER2 has been very busy, but that should be okay for us. Next here, we've got 35 which are in reserve. That means that some users have said, I want a certain number of nodes for a specific time on a specific day. I'd like those nodes set aside for me. Could you make sure that happens? And that means that only the users who've asked for those are able to use these 35 nodes that are in reserve. And then finally, the last 11 nodes are idle. They're sitting around. They've either just had a job that's finished, or they're waiting for another job to start, or something like that. If I run it again, chances are the numbers will all be different. So you'll see reservations has gone up from 35 to 39. There's only 941 which are allocated and 11 which are idle still. So that's the sinfo command. Wrong one, sorry. Next one is, so that tells you what resources are available, and it tells you a lot about the various nodes. You can, if you want to see a node-by-node version of sinfo, you can run this command, sinfo -n -l, which, trust me, you don't want to do, but I'll do to show you why you might not be interested. And it will output for every single node what they're up to and what state they're in. There's a lot of nodes that are not doing anything particularly exciting. And it just outputs a lot of info to screen. So now let's do a quick exercise. Let's look at the resources available on the compute nodes, and let's try to find out some information like the CPUs, the name of the node, the CPUs, the memory available on a given worker node. I guess you can choose any node you want. I think 1005 should be absolutely fine, so you can just copy paste this. I'll check that it works, otherwise I'll find some other random node. There we go. So you can just copy and paste that to find out about any given node and find out its name, how many CPUs it has, and how much memory it has available. And you can choose any node you want. I remember that 1066 used to have issues, but it's fine now. At the moment, this will not give you very much anything particularly exciting, given that all of the nodes are the same. One thing to bear in mind, and one thing to point out, is where it says CPUs, where it says the number of cores, it's giving you 256 rather than the 128 that I've been saying the entire time. This is because Slurm has a bit of a quirk which is it considers all multi-threaded cores rather than just physical cores. We'll get into more details about what that is, but essentially multi-threading is a special way of making a single core pretend that it's two cores, which can sometimes be useful and can sometimes not be useful. And as far as Slurm is aware, if you ever do this, which a lot of modern processors do have, Slurm will assume that there must be two cores because the CPU is telling me those are two cores, even though there's one actual real physical core. So that's where that discrepancy comes from. The next question is, and this is a question to you, is how would you go about finding all of the nodes which are free in the system? Does anyone have any idea how to do this? One great thing that you can do to find out more information about these commands, and all of the commands that I'm going to give, are by doing man for manual, and then the command you're interested in. So here, man sinfo will give you loads of information about the various things you can check. I heard someone in chat, which might very well be an answer. Sorry about that. Yeah, that's right, logical cores versus physical cores. But yeah, so does anyone want to risk an answer or potentially give an answer for this? Or would you like to just look at the solution? Cool, I'll just look at the solution in that case. So sinfo, we've already said, lets you specify the state of a node. What you can do is you can add to the sinfo -n-l command that we talked about before, you can specify state. And actually, if you look at the man page, where is it? I can find this, I'm sure. Anyways, you can do sinfo -l minus state equals idle, and that should work, and that gives you the number of idle nodes. Cool. Now, this next bit is probably the this important bit of how do you actually launch a job. At this point, we've kind of discussed, okay, you can find out which nodes are available, which of the compute nodes are available, and things like that. How do you actually launch a job? Okay, so the first step to launching a job is you need to make sure that you're in your work directory, because otherwise, what's the word I'm looking for? Because otherwise, the compute nodes will not be happy about where you are. So I move to my work directory, and wrong tab, apologies. And from there, you can copy paste this code. I'll actually make a change to it and copy it again in the Etherpad. You can paste this code, and I'm going to use the short queue because that queue's a lot faster, which is kind of important at the moment. Cool, and I'm copying this to the Etherpad. Sorry, bear with me 1 second. Course chat. Ooh, that did not. Sorry, just making this. Actually, what I'll do is I will zoom in here. Can I zoom in? Must be able to zoom. Where is zoom? Ah, I don't think I can. Weird. Nope. So what I will do actually is, while I'm doing this, I will queue my job. So the way you, that seems silly actually. I will finish editing well, formatting this. So what this job is doing is it's going to run on a couple of nodes. And it is going to, right, let me make that bit better, and let me, the rest of that's fine. Cool, there we go. Sorry about that.
But in the you got the modular EPC env thing at the end still left over. EPC job env, I think.
Oh yes, so I do, yeah, that's right. Well spotted. Cool, so what is this job doing? And let's look at it here. This job is going to be run on the standard partition. There's only one partition on ARCHER2. I'm submitting it specially to the short queue as opposed to the standard queue. I am specifying a reservation because the way that the short queue works is that there is a special reservation for it, and that reservation name is short QoS. And then what I'm doing is I'm telling it I want to run for 2 minutes, so 000200, that's hours, minutes, seconds, because this is quite a quick job. And then I'm telling it the resources I want. I want 2 nodes, and I want Slurm to know that I think each node has 128 processors, 128 cores. Yeah. Then I'm saying here, hint, no multi-thread. It's to tell Slurm, I don't want you to consider multi-threads. I want you to only think about physical cores, not logical cores. This command is to distribute the jobs across the processors, so across the cores. So essentially what this command is telling Slurm is it's saying when you're sending jobs to the various cores, I want you to fill up all of the cores on a given node before you even consider submitting 2 codes on any of the other nodes. So I want you to fill up one node before you fill up any of the other nodes, and once you've filled up that node, fill up the next node, etc., etc., etc. The second one is to do with NUMA regions, which I'm not really going to go into other than to hand-wavily say that in a node, there are special memory regions where the processors within, the cores within those special memory regions can communicate a bit faster. And I'm telling Slurm, make sure to fill up one of those special memory regions on a node before filling up any other memory region on that node. Then we load the modules. As I said before, when we were talking about modules and ARCHER2 architecture, there are no modules, or there are very few modules loaded by default on the compute nodes. So this is a general command that you should have, which lets you load the which will allow you to access the modules that have been created for ARCHER2 by the ARCHER2 support team. And then finally, for this, we'll be running a very simple job called XT-high, and actually I want XT-high version 1.1. I'll change that in the thing as well. So I'm loading the module for XT-high, and then I want to run the XT-high module. I can submit the job by running sbatch and then the name of my submission script. And then I can look at my queuing job by running sq -u and then $user. And you can see when I typed that command, the job was in the process of running. So what does it say? Here's my job ID, 167613, which is the same job ID as I was told when, the submitted batch job and then that number. It's been sent to partition standard. Its name is sub.slurm. It's been submitted by this user, which is me. Its status is running. It's been running for 6 seconds, and it's been running on 2 nodes. And here it tells me which were the 2 nodes that were used. If I were to run this again, this is such a quick job that I'm fully aware that it's already finished. Let me quickly copy the sq -u user into chat, because that is a brilliant command that you should have in your arsenals. That really helps. What's the word I'm looking for? It makes it a lot easier to check on your jobs. Just finish that, and boom, there we go. Okay, cool. So if I run ls, you'll notice that there's a new file here. I had the sub.slurm file, which I created to run my job. There's the this is work file that I've got here to make you all always know that I'm in work whenever I do ls. And here there's a new file called slurm and then the job ID 167613.out. And if I look at slurm 167613.out, this is all of the output from the job XT-high that I run on the nodes. So, okay, let's have a quick look at it. What does it do? All that this job does is it's a very simple job to check that the cores that the cores are assigned in the appropriate place. So if I was to run a job which wasn't XT-high, I wouldn't, but using all of the prefixes that I talked about a moment ago, I know that they would be in this specific order. So it tells me what both of the nodes that I've used are. One of them was 1567, one of them was 1632. Each of them had 128 cores. I was running with mainly, with only MPI and an OMP of 1. We'll get into more about what that means tomorrow. And then it says, okay, the first node to say anything is the first core to say anything is on node 0. It has rank 0, so it's core 0. It's thread 0 because this is not multi-threaded. And it's actually the physical core 0 on that processor. And it's telling me, this is telling me that all of the cores are attributed the way I would have wanted. Right, so that's how you run a job. I've kind of quickly explained what the various what's the word I'm looking for? What the various commands mean, but you can find more details about the commands here or as well on the ARCHER2 docs. If you go on the ARCHER2 user docs and then go on, it'll be in using best practices, running jobs on ARCHER2. There will be loads of information about using Slurm on ARCHER2 to submit jobs. So we've submitted using sbatch. Given the time and given that we're due a break, I will keep going and come back to this question if we have time. We've discussed how to check the progress of your job. One thing we've not talked about is the scancel command. Scancel is, let's say I've submitted a job. Let's just resubmit that job. And I realized, oh no, I don't want to run it. I can do scancel. And if I'm fast enough, which I'm probably not in this case, I'm definitely not at this point, I can cancel the job this way. And if I do sq -u $user, the job's finished, but that's because the job was probably finished anyways. These are quite quick jobs, so it's going to be hard to cancel in time. But if I'd done it fast enough, it would not have run to completion. Unfortunately, in this case, it has run to completion because it's a very quick job. Let's get rid of those. Those of you who are used to running on local systems might have noticed one particular oddity about my submission script, which is here, where I say srun, I do not specify the number of cores that I want the job to run on. And the reason for this is srun, unless you specify a number of cores, will assume you want to run on whatever you've asked for. So in this case, I asked for 2 nodes with 128 cores per node or tasks per node. It will assume that I want to run on 256 cores. I could specify the number of cores by doing a minus, it would be minus n tasks, equals, and then I don't know if I want to do it on like 128 instead, which would be a waste. I could do that. And then hopefully, yep, it seems happy with my job. It's currently pending. I can run another nice trick if you're running quick jobs and don't have too much time. You can do watch to see how your job changes over time. So I could run this, and then hopefully this will only run on 128 node cores, hopefully. I'll leave that in background whilst keeping going. But yeah, so that's the interesting thing about srun. The other thing that srun is quite good for is, okay, this is taking longer than I can. There we go. And now if I do that, yeah, there's nothing queuing. And there's no output file because it never even started running. The other fun thing about srun is you can submit a job where you've written your entire submission script by using spatch. But you can also use srun to run a job directly. So module load xthigh 1.1. And now I could do srun -- account equals ta017 partition equals standard. QoS equals short, reservation equals short QoS. That's misspelled. Reservation equals short QoS. What else? Time is a good one. Equals 000100. Nodes equals 1, hint equals no multi-thread. So I'm basically typing all of the things that I typed that were in the sbatch script. I'm probably missing a couple. Tasks per node equals 128. And what's the last one? I always forget the last one. I'm cheating. Distribution equals block block. And then I can do the name of the executable, in this case, xthigh. And if I press that, this is currently queuing. And now it's run on one of the, and I'll show you that it's run on one of the backend nodes. It's run on node NID 00103, even though I am currently on node UAN 02. So there's two ways that you can submit a job. You can either use sbatch and create a submission script, which is the way that we strongly advise you use. And then there's just directly running with srun. I heard a couple of questions. I'll check if. So one of the questions from Pedro is, some HPC demand requesting memory. How do we calculate that? The max memory, the max is the sum of the memory of each node. Yes, so that's entirely correct. In this case, you can ask for most of the 256 gigs of memory per node. So if you're asking for 2 nodes, you'll have roughly 512 gigs to use. However, there's going to be some that needs to be used just by the system in general, so you don't ever really quite have that. And then the second question is, which is faster, MD simulations running on a limited number of GPUs or a very large number of CPUs? So GPUs, graphical processing units, are roughly speaking, they're processors that have a very, very, very large number of very, very, very poor CPUs. And when I say very large number, I think modern ones probably have definitely have in the thousands. I don't think they've reached tens of thousands yet, but I think roughly order 1,000. If you were to run on an equivalent number of CPUs, the CPUs would be, because they're more modern, they're more powerful, they're able to run better. However, getting 1,000 odd CPUs is gonna require 10 ARCHER2 nodes whereas you get that on one single GPU. So there's a bit of a payoff there. And definitely you could run at an equivalent speed on a large number of CPUs as on a single GPU. I can't quite remember the number, but it's very dependent as well on the job. Cool. With that, let me check real quick that I've not. I've talked about the standard errors in the outputs. Anything that should have been output to screen will be output in your slurm.out file when you run sbatch. If you submit jobs via the srun command, you've noticed everything is output directly to screen. And if there had been a mistake, it would have been output directly to screen. Other useful information. I don't think we'll talk too much about interactive jobs in this session because I'm already running a bit over schedule. So I'll finish this real quick by pointing out the key points, which are ARCHER2 uses a Slurm scheduler. srun is used to either launch parallel applications in a batch job submission script, or you can use it to launch directly. We strongly suggest you use the sbatch method, but want you to be aware of the other method. And now at this point, I think that the next session, I'll just check real quick, the next session is a 20-minute break, which will actually be a 16-minute break. I'm sorry, I overran. If during that session, any of you want to do the questions that I glossed over, I'm more than happy to take 5-10 minutes of this break to talk you through the answers, but this is entirely optional. Please put your hands up if you're interested in that. I won't take it personally either way. And let me hide that. So Pedro asked, how do you cycle a job submission when your MD simulation is bigger than your wall time? So quite often MD codes allow you to checkpoint your job, meaning that you can like create a snapshot or something of your simulation before you run out of wall time. There's multiple ways that you can then get Slurm to continue your simulation. You can either do the slightly more what's the word I'm looking for? You can do the slightly less efficient way of wait until the job is finished and then log in and submit job, or what you can do, something which is perfectly valid. I will write it here, but I will not run this job because it will go in an infinite loop if I do. You can run sbatch and srun commands at the end of a code. So if I were to add sbatch slurm sub.slurm, what this code would do is it would run once and then resubmit itself, run again, resubmit itself, etc., etc., etc. Obviously, this one wouldn't work because it would just go on ad infinitum and eat up all of your resources. But if I was a bit clever about it and maybe had, like, I don't know, a directory called, I don't know, cd first run or something like that, and then did the sbatch command, and then at the end of that sbatch command, I had cd second run or whatever. That's how I would do it, and then everything would deal with itself. Hope that makes sense. The srun command that I can run directly, yeah, I can plonk that. I'll plonk it in the. Is it okay if I put it on the Etherpad instead of in the group chat, just because it's a bit clunky? And note for the srun command that you will need to load the XT-high. Before being able to run it. Cool, that's that done. Cool. Copied, and can you write in chat? Yeah, I can write in chat, that's absolutely fine. There you go. Right. Were there any hands up for me actually talking about if anyone is interested in me going over the questions, please put your hands up now. Otherwise, I will let you enjoy your breaks. And we will reconvene. Yep, so there's at least one person, so I'll go through the questions. So the first question is to get your head wrapped up a bit around, default options. And actually, probably the best way to do this is with the srun command. And what this question asks is, how do you find out the default values? Are there default values? Actually, quite interestingly enough, there are a lot of values that we take as default on ARCHER2. So the best way of doing this is actually to get rid of everything and see what you need to add to run. So srun xt high, it's not happy. It's not happy because I've not named a partition and I've not named a budget to allocate to, I think. So let's start by naming a partition and see if it's more happy. Partition equals standard. Your job did not have a specification of time, and the default time is not set, is short. You can either cancel your job if you wish, and the error is unable to allocate resources, invalid QoS. So I need a QoS command. I'm going to use the standard QoS in this case for a reason that I'll get to in a sec. And now it's running, or at least it's queuing. I don't want it to queue because I want to get some information about this job. So instead, let's go in sub.term. And at the moment, the only things that I had were a partition and a QoS. And the QoS was standard rather than short. There we go. And now if I do SQ, if I do a nicer SQ, which just shows my job, what does it say? It tells me I've got a job number and it's happily queuing in the standard queue. Now there's a really awesome command called slurm account, which is SACCT, where you can run -J to specify a job number, and then it'll tell you information about that job. And I can do then -L to get the long format and -- format. I can never actually remember the options for format. Boom. I'm hearing a clink. Let me check. Oops. I am trying but failing terribly at protecting you from the tunnel. The chat will be available later. Unfortunately, the chat gets erased whenever you log out and back in, so it doesn't keep for an individual. It doesn't stay for an individual. However, everything that we write that's important in chat, we also keep in the Etherpad. Where was I? Yeah. So that tells me a way more information that I want. What I want is the job ID. I can never remember. I want time. Where's time? I can never remember time. I could just look at the solution. There is a really easy way of doing that. There we go. Ah, there you go. It's time limit. Should have guessed. So I can do -- format equals time limit. Fine, I'll get rid of that. And there it tells me that my job has a time limit of 1 hour. So from that quick just getting rid of all the information, what was I able to find out? I was able to find out actually SQ -U user it won't have run yet. Oh, it did run. Oh, that's exciting. what was able to find out? So this is the SQ that I had before. The number of nodes by default is 1. The default time is 1 hour. Wrong window. The n tasks per node, well, I can just look at the output to see that the n tasks per node is 128. The nice thing about XT-high is it just gives you the answer. So it's going to put 1 task per core, or 128 tasks per node and 1 task per core, essentially. Yeah. We found the time limit using this. And then finally, we know the partition must have a, the only 2 things you need to specify are a partition and a QoS, because we were able to show that with the earlier srun command, which this one ran perfectly happily. So that was the first of the 2 exercises. And the second of the 2 exercises is the second of the 2 exercises is talking about NUMA regions from memory. Oh no, it's just talking about running on. Yeah, I feel that this is an exercise. We'll be talking more about this exercise tomorrow and in more depth, so I'd rather leave that for tomorrow and finish here. What questions does anyone have that they want to ask about what I've just talked about? I realized that there was a lot of information condensed, not a very lot amount of time. And if there are no more questions, and please always send questions if you have any. We are more than happy to answer them. But if there are no more questions, I believe we are returning at in 5 minutes, where Arno will be talking about parallel computing patterns. I'll stop sharing my screen and leave you all to your breaks.
Okay, so get started. So I think by now it's pretty clear that high-performance computing is very much about parallel computing, and a big part of the reason, main reason why we're able to get a lot of performance out of high-performance computers is because we can use lots of cores, lots of processors in parallel. So in this talk, the idea is to in order to some of you might be programmers, some of you might be using a lot of software, but the point is, regardless of whether you're a programmer or user, if you're not yet that familiar with HPC, to better understand either the software that you're already using or to make choices about what software to start to use or use in future, and also what kind of machines you could use, I think it's valuable at this point to get a bit of overview about how software does parallel computing. In other words, how does software manage to make use of hardware, namely all these processors, in parallel? And what it comes down to is really understanding parallel computing, which is a case of understanding A, what is a scientific problem? B, how does that scientific problem get somehow divided up in a way that it can be solved in parallel? And then C, how does that work that's split up in parallel get farmed out and, in a very practical sense, actually executed properly in parallel? So we're going to look at this in a kind of an abstract way by looking at patterns, common patterns that are observed in software that's been developed over the last few decades. And these are patterns in approaches to decomposing work, whatever that work may be, to execute in parallel. So first of all, as a basic much pretty much what I already said. So why should you care about understanding parallel computing and software, how software does parallel computing? Because it'll hopefully help you make better choices about what software to use and how to use that software on high performance computers. It might even help you use your laptop better, because even your laptop is already a parallel computer. So ultimately, this should benefit your research, or help you provide better support to people who are doing research, of course, depending on what your role is. So I skipped ahead. Yes, I have skipped ahead. So taking a step back, well, we said parallel computing. Do we mean talking about parallel programming? No, not necessarily. This course, as we've said at the start, is not here to teach you how to program in parallel, but it will provide you with an overview of some of the ways that this is often done. You've already seen some of the terminology, that is programming terminology, sneak in into the what we've been talking about, like MPI, like OpenMP. These are programming programming models, essentially. So these have been mentioned. So even though you're not going to be programming necessarily in parallel yourself, it's useful to be aware of these terms, because you come across them, you read the manuals, you read the GROMACS manual, and you'll see mention of MPI, you'll see mentions of OpenMP, you read manuals of software. So it's useful to know what these things mean, so that you can actually interpret the documentation to run these things in parallel. So I said we're going to look at parallel computing. So yeah, we're going to look at the first aspect of these two aspects, namely the abstract sense of how this work can be split up and how that's commonly done. So when it comes to splitting up work, I mean, why are we splitting up anything that we want to solve, simulate, model, compute? We're doing it to get an answer more quickly. So the whole goal of splitting things up and to take advantage of parallel computing is to get an answer more quickly, to solve problems faster. So I've already said we need to split whatever your application, whatever piece of software does, up between different processors. Don't worry too much now about the distinction between processors and cores. For the purposes of, in this abstract sense, it doesn't really matter whether we're talking about processors or cores. We just know we need to split stuff up. How fast can we expect things to be? Well, there'll be some more about this tomorrow, but ideally, if we ran something on p times as many processors or p times as many cores, we would like it to go p times faster. That'd be great. However, as we'll probably realize, not all parts of the work that a piece of software is trying to do can successfully be split up, and splitting up some computational work into parts may introduce some new overheads, some new costs, depending on how you split it up, which can have an impact on not reaching that sort of ideal performance. So basically, that's what I'm saying here. So how you split up computational work into tasks that are meant to run in parallel is critical, because the way to do it is that ideally, in an ideal world, you would split up your problem in such a way that each task can run completely independently of any other task. Why? Because that means that you just need to, given the architectures of HPC machines that we've sketched out, we've said, oh, it's nice, it's slow if cores need to get memory from other NUMA nodes, so need to access memory that's not in the same NUMA node. And also it's slow if distributed memory nodes need to communicate between themselves. So ideally, there would be no communication needed at all. Every task would be completely independent. At the beginning of the calculation, each task would just be assigned a core, assigned a processor, run until it's finished. That would be great. Now, would that be the total picture of perfection? No, because also each of these tasks better be somewhat taking roughly the same amount of time. Otherwise, if one of them takes much more time, then all the other tasks are already finished. And if you do nothing more clever than just statically assigning to all the processors in the beginning, then all of them will be waiting for this one task or a few long-lasting tasks to finish. So there's an idea of limiting communication or limiting information exchange as being some kind of ideal, and also balancing somehow the workload. So this load balancing is a term that will come in and again and again. Load balancing is a big familiar term in parallel computing. And the amount of communication, and in particular, the amount of time spent on communication relative to the amount of time spent computing. That's the big thing. Because if you spent, some time communicating, but it's very small compared to the amount of time spent computing, you don't care. So there's kind of a tasks, problems, and the way these problems can be split up into tasks using different decomposition approaches fall into somewhere in a regime of how they are in this sort of ideal versus non-ideal. The ideal case, or it's called embarrassingly parallel sometimes, I think it's nothing to be embarrassed about. If a problem can be parallelized this way independently, that's great. Sometimes people say trivially parallelizable. Great, it means we can use the hardware very, very nicely and it's no problem. These things require very little no interaction. Tightly coupled problems, and this is sort of a term that's a useful term to remember, tightly coupled simulations, tightly coupled computations constitute work that, if you break it up into tasks, those tasks are still quite tightly coupled. They still require quite a lot of communication between them in order for them to be computed. Now, the trivial parallelizable, or on the sort of more independent end of the regime, one example of this is probably the sequence alignment practical that we're going to be doing starting later today, after this talk, in fact. But most problems lie somewhere in between these two extremes. So let's look at a number of general patterns for decomposing computation in parallel. So how you can decompose problems depends on the nature of the problem, and also on practical aspects about how hardware can handle the way you've divided them up. But anyway, over this historical development of software that's using parallel machines, some approaches have emerged. One very common approach, which you may be familiar with from molecular dynamics, if you're running a lot of molecular dynamics, you may have read about it already and be very familiar with it. But if it's new, great, then we're telling you something new, which is geometric decomposition, or spatial decomposition, just two different words for the same thing, where any problem, any scientific problem, where the problem you're trying to solve has a natural spatial aspect, one-dimensional, two-dimensional, three-dimensional, whatever it is, well, more dimensions if you're doing something fancy. The idea for very intuitive idea for dividing it up is literally taking it and saying, okay, I'm going to literally pull this thing apart. I'm going to take one spatial part of it is going to be computed by, a processor or a core there. Another part is going to be computed somewhere else. They're just pulling it up, chopping it up essentially into lots of bits. When it comes to simple 2D weather map, you can imagine, okay, so they've got the UK there, so you're chopping up into cells that land mass, and you're going to simulate the weather above the UK, say, if it's only the land weather that you care about. An example for biomolecular simulation, you've got some protein in a solvent, and there what you're trying to do is, okay, you're trying to divide up this three-dimensional space in some way. And you can already see that the 2D map just looks simple, square. The decomposition in the case of the biomolecule, and this is an older decomposition from 2015, they have a newer decomposition by now, already looks a bit more kind of, it's slanted, so it's tessellating in a slightly unexpected way, and so they've done something clever, and we'll get into this. So in the simplest case, naive case, you chop things up, everything the same size, and you just assign one chopped up bit, one cell, per processor or per core. However, that probably doesn't give you much flexibility in order to be able to adapt to problems that are leading to load imbalance and that might need to communicate. So a more adaptable situation is where you choose the size of these cells to be variable. So because why? Because essentially, we'll get into this in a minute, but essentially if the problem you're trying to solve, the scientific problem you're trying to solve, is completely spatially homogeneous in its computational intensity, then chopping things up identically is of course fine. But lots of problems aren't. The UK is not spatially homogeneous. This biomolecule is not spatially homogeneous. So you can imagine, you can imagine that some parts of the system, for example, in the biomolecule, there'll be some active sites, there'll be some stuff going on, there's a lot more work there than in an equally sized volume of the solvent, for example. So there's clearly big differences So I'm jumping back and forth a bit. Clearly big differences, that's where we were. There's clearly big differences in the spatial distribution of the work that needs to be done. So you can imagine it's good for schemes for decomposing work to be able to be variable. And another aspect is it's good to have more cells than there are processors. Why? This is a question of granularity, which having more cells, it's kind of an oversubscription idea. Having more cells buys you something in terms of load balancing, and we'll see why. When it comes to communication, something to keep in mind is that the way you chop up your problem, spatially, means that if there is a communication that needs to happen between the cells, for example, in the case of weather, temperature, exchange of temperature, pressure, and humidity between adjoining cells, in the case of biomolecular simulation, adjoining cells, the atoms in adjoining cells need to know about, atoms in any cell need to know about atoms, whatever distance within a cutoff distance away of atoms in charges in adjoining cells. So there's clearly communication. The way that you chop things up affects also the amount of communication that's required. So you have to somehow be clever in how you do it. So this is where we come into the costs of not being clever, or basically seeing where, what are the balancing, what are the things that pieces of software that you're using that have done this, what are they trying to balance? So when it comes to granularity, if we split up a problem spatially into lots of little bits, then that is good from the perspective of load balancing, because what it means is that we've got many more cells than processors. So if some of them take a little bit less time, then that's fine, because then that means there's plenty. When those processors processing those ones that take less time are done, they just get many more of the cells that are left to process. So that there's that granularity and oversubscription allows you to compensate for the load imbalance. However, there's a danger of that in granularity, because as you're increasing the number of cells, you're also increasing the amount of communications that need to take place, because you're increasing the number of the interfacial area, essentially, total interfacial area, which is a kind of a measure of communication intensity, I guess, that's there. On the other hand, if you have chunks that are too big, then you are really going to suffer from load imbalance. You don't have this flexibility of adaptively assigning the work to processors that become free. You are minimizing communication, but it's the other extreme. So depending on the problem, depending on the software and everything, even depending on the particular kinds of interactions that you're running for a particular molecular simulation, the optimal choice varies, and it can vary dynamically during the computation or during the simulation as well. What is an effective way when it comes to communication? What is an effective way of performing this? It comes down to it's inefficient from a hardware perspective to have lots of small messages being sent all the time. So instead of that, what these kinds of codes usually do is when they split up the problem, and it doesn't need to be spatially identically sized, but however they split it up, they periodically exchange, say that if it is something that does time evolution, you're talking about a time period, they periodically exchange the values across the entire boundaries, and then these boundary values of these cells are referred to as halos. So these kinds of codes means that they compute all the stuff on the inside of each cell, and then periodically all the processors responsible for all the cells exchange information about their boundaries. That's kind of the least ineffective way to do it. Of course, you can try and make it more effective by choosing cleverer boundaries, but that's another thing. So this is just restating the load balance that I've already explained. So no need to say the same thing again. So you can measure the load imbalance. Maybe touch on that possibly tomorrow a little. And there are techniques, like I've already described. You can compensate for this, and you can do it. You can try and compensate for this statically, or you can continuously load balance as the computation simulation proceeds, which is known as dynamic load balancing. So that was the first decomposition model. Let's look at another one. Another common one, which actually is maybe a bit simpler even to understand. And I apologize for the terminology, politically incorrect terminology, which should have been revised, because the idea of using words master worker is no longer up to date with what's convenient, what's current. But so here the idea is that what the problem that you're trying to solve, the work that you're trying to do, whatever it is, it doesn't have to be spatial, just whatever it is. It could be a database, it could be whatever it is. The work is split up into distinct tasks, and those tasks are independent. And if they are independent, so if you're in this really kind of nice, easy regime in a sense, then all that needs to happen is that some processor needs to be responsible for assigning all the tasks to each processor that's actually doing the computational work, and then gather that together. So then there's one process, a master process, which sends tasks to the worker processes, and these then compute and send results back. And if you do a similar thing with having lots more tasks and workers, you can do a same load. You can achieve the same load balancing thing as you get conceptually with the having more cells than processors that I've that I outlined for the geometric domain decomposition, because you take the workers that are finished quicker because they have a task that doesn't take as much effort, can just take on more tasks. So the consideration here is there might be some communication, is much less clearly than in the spatial domain decomposition, because there's no there are much more independent tasks, so there's much less communication. However, there might be some, and if there are too many workers, there's a limit to the scale, because you might need to scale up the number of, if there's too many worker processes compared to these master assigning processes, then the master process can become a bottleneck. So you have to expand possibly the pool of these processes that assign, so you have to do more bookkeeping. There's questions of resiliency as well. So there's still things need to be considered here. So there are some communication overheads. If the tasks are not totally independent, then these overheads can quickly overwhelm the method, the approach. Another approach, again, kind of just conceptually, is quite, some of them are very intuitive, spatial, and this is just an idea of a pipeline, which is pretty abstract, and it can have a form, it can be used for many different kinds of concrete cases. It's kind of like General Motors, Ford production line model, or actually there's also a model of chip design that was used in early processing called systolic processing, before the kind of processors that you'll learn about tomorrow were common. Idea is that you've got a number of processors. Each stage there is a processor doing some work. It's doing the same work. It's just that it's constantly getting fed new data, and the data that's being worked on goes through a pipeline of successive stages. So some scientific work, engineering work, some computational work naturally has this property anyway. Some work can be reformulated in this model. So there's this kind of flow of data which matches quite naturally in some cases. This is just highlighting, just illustrating, I guess, the idea. Now, what you do have to take care of course, is that you want to balance each stage could have balance, could take more time than a different stage, so you could assign more processes to that stage. So there could be some aspect of dynamic load balancing here. Again, these are just very, very general abstract sketches. You can imagine how they might be adapted in particular cases. In a kind of roundabout way, the actual architecture of how some CPUs are designed have an aspect of a pipeline within the actual processing, within the execution of instructions of machine code. Software ultimately gets translated into machine code, very simple basic instructions that the processor executes, and it executes it actually as a pipeline of instructions being fed into this actual unit that performs, that reads the instructions. The instruction gets fetched, they get decoded into what they mean to execute, and then they get executed, and the result gets written back. So there's actually some of this going on at a hardware level as well. Another example, more concretely, of this kind of pattern is I've seen some examples of some bioinformatics, simple bioinformatics workflows or general data processing workflows using Linux shell command line, where series of piped commands feed into each other, and then often, well, we'll get into that in a couple of days' time. Some of the issues that can arise there. So these kind of pipelines can be combined with other decompositions, and it's just quite a general model. Another model that we see a lot of, and this is kind of actually a very concrete model, because it maps very directly onto how a lot of software is actually programmed in a lot of programming languages that have been used for scientific applications, namely the good old for loop. So a lot of programming languages have a construct, a syntax, where you say for some iteration, iterate lots of times and do the same thing. And these are often actually the most numerically intense parts of scientific codes. And some of these loops are very, very easily amenable to being parallelized, because what you can do is, if a loop has 10,000 iterations, then if those iterations are independent of each other, then clearly 10 cores could just perform each a tenth of those total number of iterations. And yeah, there's various kinds of, as a programmer, you might need to take responsibility for judging whether or not they are independent, but the point is that in principle you can do this, and there are fairly straightforward, well-established ways of getting making this happen directly. Yeah, so the details about why this is suited to particular cases is you can just say that they are sometimes not suited or sometimes better suited, but without going into the programming details or particular cases, you can't really say why. This is a common pattern, and it's used. It's easy to apply by the compiler often, as we so I think Holly might mention in a couple of days, tomorrow. Okay, so the summary of this session is basically to give you a very rough, abstract sense of software that runs in parallel. It's always doing some scientific problem. Maybe from the software you use, it's trying to solve some problem, whether it's molecular dynamics or something else. It somehow has to split the problem up into tasks. In doing so, there are patterns that have emerged, and these patterns have emerged to flexibly meet the challenges that are imposed by the constraints of the hardware, the NUMA regions, the communication over an interconnect, etc., etc., etc. And software needs to be very flexible. It has had to be flexible over the decades, if it's existed for decades, like a code like GROMACS has, for example, to adapt to new architectures that have different trade-offs in terms of how much the communication costs are, how much the memory. Sometimes the memory certainly gets much quicker for transferring data to the processors. So these things change over time, and there's a lot of research that has gone into making these decomposition approaches varied and very clever. So maybe during the GROMACS practical, Julian might mention that GROMACS decomposes things in really funky ways, and it does it to minimize communication. So there's all these schemes going on. But this helps you hopefully to understand some of the underlying things that software is trying to do for you. It really is trying to do all these things for you to try and be fast. But you have to sometimes try and help it by appreciating a little bit what it's trying to do, reading the documentation, seeing how you can, push and pull the levers to make it run well on whatever machine you're using. And that could be your laptop even. It doesn't have to be a cluster or an HPC machine, although hopefully it is if it works well there. So that's it for that. Have I got not yet gone over time? Great. Okay, before I go to describe the practical, are there any questions? Since we have a couple of minutes anyway. Any questions about that? Okay, I guess not. That's fine. Right, so then we may as well launch into practical. Possibly depending on your time zone, and you might think, okay, well, getting a bit late now, but we'll start by describing the practical. You can get stuck in, and it's the first of 2 practical sessions on this. Basically, tomorrow morning will be continuing the same practical, so we can start it and then see how we get on. Okay, so this is the first practical where you actually get to play around with the code and do some stuff in ARCHER2. So this is a practical aimed at doing genomic sequence alignment, and ideas to get used to actually using the machine and appreciating how a real package runs in parallel, looking a little bit at how to make it run in parallel in the way that you want, understanding that it's using threads, understanding that it's using something called MPI, which you'll gradually, tomorrow as well, get more of an appreciation of. And it should relate to what we covered in the last, covered already today in lots of the talks. So what the application in question is called Hammer, or rather that's a suite of tools, and the particular executable, the particular command that you're going to use is called phammer. And the idea is that it queries a protein database for matches with a given protein sequence. So you say, okay, with this database, I've got a particular sequence. Can I match it? What are the how well does it match? And just a bit about it, because I don't know anything about this, but just for anybody who is bioinformatics, genomics kind of person, this might mean something. BLAST is, I think, a very familiar method. But phammer is an alternative to BLAST. Sequence alignment. It uses a hidden Markov model approach to build some kind of profile representation of the sequence, and to do a very particular kind of querying algorithm against the database. It's got some fancy filter for probabilistically assigning scoring, alignment scoring against the database. And okay, so it has a number of top scoring matches, and then you choose the thresholds for how strict you want to be. So there's some of these settings that you play around with. So if you're very strict, you'll not get very many matches. If you're less strict, you'll get more matches, which can then also mean that influences the runtime, which is one of the things that you'll play around with. So phammer, it runs in parallel, otherwise we wouldn't be running it. And it runs in parallel, or it can run in parallel in two different ways, which are mutually exclusive. It can run in parallel, i.e. use multiple cores, using threads. Now, as will become clearer tomorrow, when we talk about building blocks, software building blocks, threads are restricted to shared memory space. So what that means effectively is that, given what you know about the architecture of ARCHER2, that means essentially they're limited to a single node, i.e. to 128 cores. So that's one mode in which you can use phammer. So you'll use that first and see how far you get, or what the result is, of how well it performs. And then using another parallelization approach, using something called MPI, which you've mentioned a couple of times already today, which is basically getting phammer to exchange messages between multiple instances of itself that are running concurrently on cores that may or may not be located on the same node. Because these are messages being sent, rather than threads trying to access the same shared memory, this should be able to, this can run across shared memory nodes. So it can, cores on one node can send messages to cores on another node, so it can run on many more nodes. So you could use to see how fast you can speed up the biggest problems you can run. Both of these models underlying it use a kind of a task farm or work queue model, which is one of the decomposition approaches I just talked about. So I said that the sequence alignment. So you can imagine what's going on. It's taking a small sequence and it's going across the whole genome or collection of genomes, whatever it is, to compare it to each bit. You can therefore imagine that the target the database that you're matching against, you can chop that up quite trivially and just match against parts of it. So essentially, that's probably kind of what it's doing. That's my rough understanding anyway. It says these concepts will be explained later in the course, but the MPI and threads will more, but the task form work queue model was just explained. So the practical, there's an instruction sheet which is in the I'll put the link in the chat as well. So you log on, you download. We're getting you for not providing this as a module. We're not making it too easy. We're just saying, okay, you have to go to the website, download the source code. This is getting you experience doing all the things that you might need to do, unless your HPC systems team has been so kind to provide the software already in a module. We're getting you to compile it, and you might not realize what's going on with compiling, but Holly will explain that tomorrow, I think. Then progressively you'll go from running a serial on one node to running a parallel using threads, etc., and then do some plots of performance. So I'll just grab the link from the GitHub page, link to the instruction sheet. Okay, so you're welcome to come get on started with that, get stuck in, and we have, so what we'll do is see how it goes, ask any questions you have, and at 5 to the hour, we'll do a quick, 5 minutes up to the upcoming hour, we'll do a quick recap of today. I'm just looking at tomorrow, and I'll ask you, any feedback, any things you'd want us to focus on tomorrow as well. That's it from me for now. Any questions, just let me know, let us know. Otherwise, get stuck in and actually run stuff on ARCHER2. Yeah, threading is restricted to a single node. It might become a bit clearer tomorrow why, but it is because threads are managed by so threads exist within a process managed by an operating system, by an instance of an operating system that's running. And as we already described, kind of in the HPC architectures talk, what distinguishes, one of the things that distinguishes shared memory system from distributed memory system is that there in a shared memory system you've got one single running instance of an operating system that accesses and controls all the memory and all the cores. Anything that therefore it cannot directly access, it cannot manage the execution of threads that somehow need to share the memory space. So basically the point is that there's no kind of the definition of a node, if you like, in this case is a shared memory space. So it's kind of it's almost like a circular definition, but yeah, these threads exist within an instance of the operating system. They're managed by the operating system. Therefore, the only memory they can access is memory managed by that operating system. And if that operating system is not, connected up to another node so that it can access the memory there, which is not the case, then they cannot. It doesn't exist. It's outside of their universe. They don't know anything else. Threads don't know anything else than the operating system to which they belong. That's their universe. Maybe that will become a bit clearer tomorrow, perhaps. Is that any clearer? Not really. Okay. So processes, on the other hand, I mean, sending messages is different because messages don't use the shared memory space. They, so if there's two processes, each on a different node, each managed by different instance of an operating system running, they both inject, they kind of just inject out messages via interconnect. So the operating system of process A just says, okay, I'm going to send a message out via this thing that I know exists, which is this network interface. So I'm just going to spit something out to the network. that's it. The network has to take care of the rest, and then it gets in some messages from the network, which, because the network interface speaks to this operating system in which process A is located. Meanwhile, process B and C, D, E, F, G, etc., they all have their own operating systems and are also just spitting out and receiving messages into, well, not the void because they get an answer back, but they're spitting out and getting back from this network interface, which is connecting different running instances of operating systems. So that's kind of the difference. And I just realized gesturing is useless if you're not showing gesturing. So if I answer a question, I should show on camera because gesturing sometimes helps, but it's no use if you're talking. Yeah. Just curious, has anyone managed to build Hammer yet? If you built Hammer, could you raise the hand? Okay, just out of curiosity, how many of you happen to know that you can build something using make in parallel to speed things up? Did you use that make-j with some value of j greater than 1? If you don't know what I'm talking about, you can forget what I said. Just curious to see if anybody has any experience with that. Okay, yes. We got it from BSc, of course. That's no surprise. Yeah, I'm that cool. Okay, nice. Yeah, you have to use. Yeah, I mean, make's very useful. Writing a make file. I mean, it's quite. Once you get down to it, it's quite a sort of nice thing to have. Yeah, Richard, you can. Yes, you can. You should be able to. I mean, we have this reservation that's active between this morning and until 4, I guess, UK time. But that's right, Julian, isn't we can just, it's not charged, so people can just submit jobs whenever, right?
Yeah, that's right. You just need to not use the reservation, but that's getting rid of the line. If you have any questions, send me an email.
But yeah, Richard, you'll just have access to ARCHER2. In fact, there'll be lots of opportunity for you to use and try out everything that you've learned in the course, because there's going to be continued access until, what was it, about a month from now? You set up, Julian?
That is correct. Everyone attending this course will have access to ARCHER2 for, oh, you'll still be able to log in for a long time afterwards, but there will be compute time. I think we have about 1,000 node hours for this course, and anyone on this course is welcome to use any amount of that that's available at the end of the course to play around on ARCHER2, see whether it's useful for your systems, get a better handle on using HPC facilities and that sort of thing. And that budget is available until, I think, the 22nd of April, but I'll check that.
Cool, thanks. Yeah, so what I'll try and do is, I mean, give people a chance. Obviously, I mean, people are working on this now, and then tomorrow morning is another session. But I'll do towards the towards the end of that session, maybe the last 5, possibly 10 minutes of that session, I'll kind of try to wrap up and do a comparative kind of take-home message from some, what we can get out of it. Yeah, just a chance to work on it now and until whenever you like. Just out of curiosity, who already knew Hammer? Okay. Yeah, I guess I guess we're less privacy conscious. I don't know. I mean, it's some sites just seem to some sites are very they don't show other people's jobs. ARCHER2, yeah, we do. It's I guess it's kind of I'm trying to think some of the German machines I've got access to as well. They do a similar thing. They also don't show it. It's a bit messy, yeah. Well, at least you can, yeah. It is a bit, well, okay, so there's 2 sides to that. You can see that the machine is being used and you're not the only person on the machine. On the other hand, some people then start to look at other people's jobs and saying, hey, hang on a second, this guy, girl, they've got so many things queued. They're just taking up the queue. And why is their job starting to run now and mine hasn't? And it's been here for ages, which is a fallacy because, as I tried to describe with the scheduling policy, the ways of the scheduler are weird. The scheduler can do things that might not seem obvious. Why?
Hi, can I make a question?
Yes, of course.
I think it's too complicated to type.
Yeah, sure.
So it's saying here that Archer login node has 128 cores, and we can use it for running small tasks. And here it is giving the example of 102 use with more than 1 CPU. So how is that managed by the system? What happened? Is it
Yeah,
12 or 128?
So I have to admit I don't know. I know from the past sometimes, but it changes over time as well because I'm not up to date with ARCHER2. Maybe Julian and Holly can comment. What I used to do with Archer, which is I would try to not run too long, but that's kind of like a gut feeling. If you run for 10, you get system administrators complaining or something. They put in an automatic kill if somebody runs for 10 minutes using 10 cores or 24 cores. They would get killed. Do you have any idea, Julian or Holly, what the kill is? There kill switch?
For starters, you can't run multiprocessor jobs easily on the head node. So if you were to try to run MPI GrowMath, for instance, it wouldn't work.
Just threaded, just threading on.
It's a single-threaded only. And then the other thing is, the system administrators are on the lookout for that sort of thing. I know that on ARCHER1 there was a script that would kill anything that runs longer than an hour. I think we're a bit more lax about that on ARCHER2 because there is not the post-processing nodes for long single processor jobs that we had on ARCHER1.
Ah, yes, you can tell people to use that. Yeah, I mean, it's
So I think
multi-threading work, but it's yeah.
so I think we operate in if no one complains, then you're fine policy. But if people complain a lot, then I mean, to be fair, if anyone complains that any user is running a job that's taking way too long and using way too much memory, the system administrators will kill it, and then we'll be in touch with you to say, please don't do this.
Okay, but my question is more focused about how to use the nodes and not about time. So for instance, this task that we have to run here with Hammer and CPU is just instant, like probably 1 or 2 seconds. And I can run in one node, or I can run in 128 nodes, and I cannot see the difference because the task is really fast.
Yeah, you're
But
right.
my question is, what happens if, for instance, we have now 21 people logged in, assumingly, supposedly on Archer, and what happens if everyone tries to run that really simple task using all 128 nodes? So how does that happen? Are they going to a queue? It's first
The
come first
operating,
served.
so the operating system. So I think that node is running a single instance of an operating system. An operating system will try to manage if there are more threads than there are cores. The operating system has certain default ways that it handles that. It maybe tries to switch between them. That they each get like a small fraction of time. There's interleaving. It oscillates between them, switches between them.
But what if everyone runs with 128 at the same time?
Then things could potentially slow down a bit, which is why hopefully not everybody runs with 128 for more than like a second or a few seconds.
Yeah, that one takes 1 second to run. But even in that 1 second, if everyone types at the same time, it's a queue for them. It's the first time comes base.
Yeah, no, it's not a queue. It's just it's the operating system will just everything will be a little bit slower, and it will just be churning away a bit. It'll be like a burp, a temporary burp in where
Okay.
it's slow to respond, because it just has to deal with load. So just think of it like this: when you're running lots of stuff on your laptop, so many things that I don't know, for example.
Sorry, quickly, I wanted to point out because someone's brought this up. There was an error in the example script that Arno provided. There was no QoS. I've now updated the script, so if you look at it again, there should now be an sbatch QoS equals standard line, and it should now run.
Thank you so much. This is exactly what I should have asked you earlier to look at, but it's really appreciated.
Sorry for
Okay. No, don't worry. Let's address that then. It's better than that I continue.
It's solved. Sounds like.
Thanks.
Yeah. Thanks, Julian. So yeah, there's not much point with the default settings running on multiple cores because it completes so quickly, and that's why it goes on to say, you know, let's see, there's the after you do it serially on the compute node using a job script, then at least introducing the option -- max to increase the sensitivity means that it's going to take longer to finish, and then ultimately later on you can even grab a larger data set, larger database to match against. Yeah, if you yes, if you want to use 2 cores, then yeah, CPUs per task is 2, and tasks per node stays at 1. Don't know what the R at the front of the start of your line is meant to be. R and then dash CPU. I don't know what the R.
Maybe it is easier like this. No, it's from the previous word. Yeah, but I'm trying to submit this, but it dies. I don't know why.
Sorry, Pedro, what was that?
I was saying that I added this, but then it dies when I submit. It says terminating exit code 1.
Okay, and that's in the Slurm output, right?
Yes, srun error, blah blah blah. Exit code 1.
Could you copy your Slurm submission script into the Etherpad, and I'll have a quick look, please? I can give you a link if you want.
I have it open already.
Brilliant. Cool, thank you very much, Pedro. So from the looks of it, at no point do you use an srun command. So if you, I'm editing in there, and we can take this offline if this is annoying, by the way, Arno.
Oh, it's fine.
But the CPUs per task is an srun command, so you'd need to either have srun CPUs per task, blah, 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 or you could instead do, this might work, though I'm not entirely convinced that it will. Let me know if it does. Minus CPU.
But the
equals
CPU per task should be set in should be S batch, and srun picks it up.
Equals 2, and then you should do srun still, because at the moment you don't have an srun command.
Oh, okay, okay, right. That'll be it. Yeah.
So guys, I'm stopped on the slurm command, hammer.slurm. Hello?
Yeah, what's the error message you're getting?
Batch job submission failed, requested reservation is invalid, but I already changed to QoS, and then I changed to from standard to short, but it still doesn't work.
Okay, so if you want to use short, you'll need to run.
No, I don't want anything. I just want to work. The way it was, it will work. Or maybe.
You'll need to add this line that I just typed. So sbatch -- reservation equals short QoS to run on the short queue.
Perfect. And in the standard should work only with reservation equals QoS?
The short queue will only work with reservation short QoS. The standard does not need a reservation, but we've got a reservation for the course to mean that your jobs will jump to the start of the queue and run faster. So if you were to submit on standard, given recent waiting times, you might be waiting for a while. You might not. I couldn't possibly, it really depends. But there are a lot of people running at the moment.
Okay.
And the reservation is active for another 6 minutes, I think.
Okay. So
Is that right, Julian? Did it finish at 6 or at 4 or at 5?
Yeah, it's at 4.
4, yeah. So yeah, for another 5 minutes, 6 minutes, and then the reservation will be inactive, and the jobs will just need to be submitted to standard. Sorry, I mean, not using the reservation. It's probably time we do a recap because it's almost 5 minutes too.
Yeah. Do you want to do it or shall I?
Up to you.
I'll do it because you've been talking a lot this afternoon.
Okay, cheers.
Right. So let me get the. Let me share my screen. I want to share this one. Yeah. For the next couple of minutes, I'm going to do a quick recap of the day. Hopefully today, you will all have been able to log into ARCHER2 and run your first couple of ARCHER2 jobs. You will have learned about what defines a high-performance computer, what defines high-performance computing. You will also have learned about submitting jobs to, you'll have learned the difference between a login node and a compute node. You'll have learned how to submit jobs from a login node to a compute node and other sort of, what's the word I'm looking for? Other sort of terminology which probably would have made much less sense beforehand. This was really the aim of today. The aim of today was really to make sure that you were all able to start running, that you were all on ARCHER2, that you were all understanding what we were talking about. Hopefully this is the case. And the final thing I'd like to ask from you all, if possible, is please could you either in the chat or the Etherpad let us know one thing that you felt we did well today, that you felt we taught well, or that part of the course that was interesting or well done, and one other thing which you felt we could have done better, and then a third thing which is what you would like us to focus more on tomorrow. So would you like us to spend more time on, say, molecular dynamics specifically, or would you like us to spend more time on how computers are made up, that sort of thing? Please, anything that you want. You can either put it in the chat or in the Etherpad. I will set up a thing in the Etherpad to make it easier. So 1, what did we do well? 2, what could we do better? And 3, what would you like us to focus on tomorrow? I've put those 3 questions in the Etherpad, and if you could answer, that would be brilliant, and we'd really appreciate any of those feedback. I've put the link to the Etherpad for anyone to answer. You can answer anonymously if you want. Anyways, you can answer with your name hidden if you want. We don't really mind. We're more interested in how we can improve and keep the course going well. At this point, we'd like to thank you all for coming to this course. We hope you've enjoyed it so far, and we hope you've been finding it useful and interesting. Tomorrow, to give a quick brief overview of what we read tomorrow. Tomorrow we will be talking about how to measure parallel performance. We've hinted a lot at how there are times where increasing the number of processors, the number of cores that you're using, will increase how quickly a job finishes. Tomorrow we'll really focus on how that can be quantified. We'll also be talking a lot more about computational building blocks. What do we mean by software? What do we mean by OSs? What do we mean by processes? What do we mean by threads? And also hardware side of things. We'll talk about the difference between a processor, a core, a CPU. We'll also talk about what multi-threading means and things like that. And we'll also be talking about parallel programming models and how to compile software. Interspersed between all of these lectures, we'll have another go at the Hammer practical, where at this time you'll be looking at a larger data set and trying to see how much quicker it can run as you increase the processors. Then there'll be a couple of GROMACS practicals where you'll be able to run some molecular dynamics on ARCHER2 and try to perform some benchmarking for that. I think it'll be quite interesting and quite fun, and we all look forward to seeing you tomorrow. Arno and Holly, is there anything you wanted to add?
Here's answering question. I don't think so. No. So yeah, people look forward to, if it's useful, what Julian was saying, useful if we get some feedback for anything that people want to focus on, especially. So yeah, good. Thanks everyone for sticking with. It's good to see numbers haven't dropped really, so people are either, well, people are very engaged. So that's great. Thank you all for coming along today, and see you tomorrow hopefully.
Oh, and I think one last thing to say, if anyone's still working on the Hammer tutorial, I imagine we're happy to stick around for another 15-20 minutes. Is that right, Arno? Or to answer questions if anyone has any.
Well, yeah. If anybody is around, I'll stick around a bit longer, just in case there's anything that's not clear. Yeah, sure.
I mean, if you're busy, I'm happy to answer any questions that anyone has about the tutorial.
Yeah, I know it's not very good together, so I'll stick around for a bit, just in case there's anything unclear in the instructions. Although, if it does pertain to another error in the specification, then you're probably better placed clearly than I am to solve it.
What was the other error? I didn't see it.
No, I'm saying if there is if there is something else.
Oh, right.
Then you're clearly the person to spot it. Cheers, thanks, Miguel. Nice to have you along. Array jobs. I don't think we're. Yeah, that was too advanced in a way. I don't think we were planning on talking about that. So.
Yeah, we weren't planning on it. If it's something that you're interested in, I'm happy to chat about it a bit now as an extra. But that's up to you. Definitely, there's information about it on the ARCHER2 website. and that would be my go-to solution for finding out more about it. I'll share my screen. Boom, it's that one, I think. There we go. But basically, in Slurm, the command for running array jobs is sbatch minus minus arrays, and then the number of array jobs you want starting at 0. And then you can run your job a certain number of times. Now, it's quite restrictive on ARCHER2 actually, because we don't have that many nodes. We've restricted users to a quite low number of jobs running on at any given time. I think it's 256, but I might be wrong. It used to be 256 definitely at one time.
Cutting out a bit for me, Julian. I don't know
about. There we go. Standards. You can have 256 jobs running at the same time. As far as Slurm is concerned, you can either do 256 submits, or you can do one single array job. Your number of jobs running and queuing. I think that's pretty much all there is. Is there anything else specifically you're interested in about array jobs, or does that? Great.